Welcome to track 2 of AtPesc. Yesterday was the hardware track for one day. Now for the next 3 days, we will cover parallel programming models. So it's a three-day track, three-day session. And I'm Rajeev Thakur from Argonne. This is Yanfei Guo and Ken Raffenetti also from Argonne. We'll cover MPI today. Tomorrow, Tim Mattson from Intel will cover OpenMP. And on Thursday, Christian Trott from Sandia will cover COCOS in the morning, and Rich Hornung and Arturo Vargas from Livermore will cover Raja in the afternoon. So just a couple of introductory slides about this track, and then we'll start with MPI. So, what do we mean by a programming model? It's a way in which you think about how you would express your program, and how you would write your program to the system. And what's happening underneath might be quite different from the way you express yourself, because there'll be some compiler or runtime or software underneath that translates what you write into something that the computer understands. So even if you're writing a simple sequential program which looks fairly straightforward, it could end up getting translated into something that has on modern systems, it has out-of-order execution and instruction-level parallelism and so forth. So that might be different. Now, programming models can differ a lot in their level of abstraction. That is, are they low-level where you program closer to the hardware and it's closer to what the end program looks like, or it's at a very high level where it's user-friendly and it's easier to program, but then there's sophisticated software underneath that translates it into something that the computer understands. So in the next 3 days, we'll cover 3 types of parallel programming models, because we are interested in high-performance computing and scalable parallel computing. Today, we'll cover the message passing model, where you have processes with distinct address spaces, and each of them you program as you would program almost a sequential program. Of course, you could have OpenMP in there, and you could have other node-level abstractions in there. But then across these processes, you have to exchange data when you need to, and you use some message passing model for that, and MPI is what gets used nowadays. So that's the thing covered today. Then there is a shared memory model where you need to communicate among the nodes or the processors within a shared memory compute node, say. And we'll look at that tomorrow using the OpenMP system, which is commonly used nowadays. And you can have a hybrid of MPI and OpenMP, and we'll look at that this afternoon. So, although OpenMP is tomorrow, we'll cover hybrid programming this afternoon because it ties in with MPI. You don't need to know a lot of OpenMP for it, but it's the MPI part of the hybrid programming. And then on Thursday, we will look at high-level approaches. These are abstractions for node-level performance portability. So nowadays, the nodes are getting fairly complex. You have multiple cores on the node, and you have very often you have some kind of accelerator, and this is only going to increase. It's not this style is going to increase. So the nodes are getting complex, and there are many vendors. So it's not just one kind of accelerator or GPU. There are multiple vendors with different programming models and so forth. So there are 2 systems, COCOS and Raja, that try to hide these underlying details from you and provide a higher level abstraction, and those systems translated to the underlying platform. So that gives you your code portability. You can write your code and run it on any complex system. So that's on Thursday. So these were just a couple of introductory slides on the session, and now we'll switch to the MPI. By the way, you can download the slides from this link, or they're also available on the AtPesc agenda page. And the code examples are also there. So there's a zip file with the code examples. So this is not an introductory MPI tutorial, because one of the prerequisites for this class was that you know at least some MPI or OpenMP programming. So we assume that you know at least the basics. We're not going to go through simple programs. And is that okay? Does everyone know MPI at least a little bit, or is there somebody who's not familiar at all with MPI. Even if you aren't, I think you'll still be able to follow because it's not terribly complex. And if you don't, you should let us know. And we're not going to get into too many coding details or the syntax of the functions or so much. We want to focus on concepts and what you need to do to get performance and how do you avoid common performance-related pitfalls and scalability as well. And we're going to have hands-on throughout the day, not just in the evening. So after dinner, there is a hands-on session for sure. There wasn't one yesterday, I believe, because that was the hardware track and there was no programming there. But from today onwards, after dinner also, there'll be some hands-on. And we have hands-on in each of these sessions. So towards the end of this session, before the coffee break, and then again after that and so forth. So be ready to write some code or do some programming. So in the morning, we'll look at performance issues in MPI programs, avoiding unnecessary synchronization. That is how your choice of MPI function can lead to unintended synchronization, and that can slow down your program. We look at MPI derived data types, MPI data types as a way to minimize data motion or to express your program in a way that MPI can help you get better performance. We'll look at some topics in collective communication and non-blocking collectives and so forth. Then we'll cover one-sided, Ken will cover one-sided communication, which is also known as RMA or remote memory access. I think that will not finish entirely in the morning. Some of it will continue into the afternoon. We'll see depending on how the hands-on goes. And in the afternoon, Yanfei will cover hybrid programming. That's MPI plus threads plus shared memory directly, and also accelerators. Then we'll look at process topologies and neighborhood collectives, and there are some more hands-on out there, and then continue after dinner with the hands-on as well. So just one or two introductory slides. So what is MPI? So MPI is a message passing library interface standard. So it's a specification that you can download from the MPI forum website. It's a PDF file. So it doesn't refer to a particular implementation of MPI. So when you say you're using MPI on a particular system, you're using an implementation of MPI on that system. MPI is a standard, and that's why you can write your program once and run it anywhere as long as you're following the standard and the implementation is following the standard, which they do normally, which is good. So it's a library, it's not a language. It has bindings in many languages. So you can have functions or you can interface it through C, Fortran, C++, and so forth. So the original MPI came about, it's been a while now. 1994 is when MPI 1 was released. And that has the basic point-to-point communication, collectives, non-blocking, and many other things. So many people are happily just using that part of MPI and not bothering with any of the advanced features that came after that, which is fine, but there's more you can do, and we're covering some of it here. There are portable free implementations that have been there right from the beginning, which helped MPI get popular and widely used. So this is the timeline. So MPI 1 came out in 94. Then about 3 years later, there was MPI 2, which added some extensions to basic MPI. There was a whole chapter on parallel I/O. How do you do parallel file I/O from your program? We're not going to cover that today. There's a separate I/O day, which is Friday perhaps, Friday of this week, and there'll be at least some of MPI I/O in it. There'll be other things as well. Then it added one-sided communication, which we are covering. It also added something called dynamic processes, where you could expand the number of processes in your program at runtime, or you could connect separately started MPI applications, have them connect and communicate, like a client-server kind of model. That tends to not get used so much in practice, and on many of the supercomputing systems, it's not even supported. That is, the vendor MPI implementation may not support that part because it doesn't interact well with their job scheduling and resource management systems. But if you're running on a cluster where you have more control and more freedom, any of the or free MPI implementations will support that. But we're not going to cover that here. It added thread supports and C++ bindings. Then for about 10 years, the standard was stable. The implementations kept getting better, and there were newer systems, and they supported all the new systems. Then in 2008, there was MPI 2.1, which was minor corrections and bug fixes. In 2009, there was 2.2, which had a few additional features. But any of these minor releases, after the decimal point, doesn't have too many changes. The next big one was in 2012, which was MPI 3, which had many new features like non-blocking collective functions or collectives that operated on a neighborhood, that is nearest neighbor type of communication, but collective. There were improvements to the one-sided communication. The original one-sided had some issues that not everyone liked, or there could be performance-related issues. So those were improved upon in MPI 3. There's an interface for tools to interface with an MPI implementation. So all the debuggers and performance tools can do a better job of integrating with an MPI implementation. It added Fortran 2008 bindings as well, which is the modern version of Fortran. And then 3.1 came out in 2015, which had smaller updates to 3.0. And the forum is now working on MPI 4, which might come out late. Is it this year or next year? This year is all, is half over, so it's probably next year. Yeah.
What came before MPI, and how was it not? MPI was much at advance. So
yeah, that's a good question. And in some of these talks, I have a slide before, which says what was there before '94. So starting the mid '80s onwards, these distributed memory parallel computers became popular, or there were vendors selling them, and people were also putting together clusters of workstations and running parallel programs. But each vendor had its own interface. So Intel had something called NX, IBM had something called EUI, and they changed names 2-3 times of that. Then Thinking Machines had something called CMMD. N-Cube had its own message passing system. Then there was PVM, which was a portable parallel virtual machine, also a message passing system that came from Oak Ridge National Lab. There was Chameleon and P4 from Argonne. Then the theoretical chemistry group, TCG, at Argonne had its own message passing library called TCG MSG. And we are already at 8 or so now. So there was this plethora of message passing libraries. Each of them had their own interface. So when you wrote to one of them, you wrote using the Intel version, you could not run it on an IBM system or Thinking Machines or whatever. And when one of the vendors went out of business, you were stuck with code that you needed to port to some other system. So it was recognized that this lack of a standard interface was a problem, and it was coming in the way of application development and a portable application development. So all these people who were involved in these libraries, plus the users and other researchers, got together in an informal way and called themselves the MPI Forum. So it was not an ISO or ANSI standard, but it was an informal group of people, somewhat like this, well, smaller in size, maybe 30, 35 people at each meeting, and they came up with this thing called MPI, and that's what continues now. Right? Yeah.
Yeah. And what are the main features that are coming with MPI 4?
Yeah. So we might cover that in the afternoon, and we have some slides on that separately, but. So what should we say here? There is and it gets, maybe we'll talk in the break because it might be a little distracting to others. Those are more advanced features now. Yeah.
Any talk of supporting C++ in the board or?
Yeah. So C++ has an interesting history. In MPI 2, there were C++ bindings, and then sometime I think in 2.2 or so, they were deprecated, and then in 3, they were removed as such. So officially, it doesn't have a C++ binding now, although you can use the C bindings from a C++ program. So what happened was the people in the forum who had proposed the original set of bindings and who were the leaders in that, they themselves felt that those bindings were not the C++ style, or they were not serving the needs of C++ programmers. So they themselves wanted to get rid of them because people were using the Boost library and whatnot. So right now there is no officially a C++ binding, although the implementations have still kept the old ones. They've not deleted them, so that they don't want to break the old codes. But the new functions may not have the C++ binding. So right now, you have to use the C bindings through a C++ program. I'm not aware of an effort to create a new set of C++ bindings. There may be talk about it, but I've not seen even one page about it yet. By the way, the MPI process is all open. You don't need to be a member or pay a membership fee or anything. So you go to the meetings.mpi-forum.org website, and there are all these working groups and the meetings, and there are some virtual meetings also which are like a video conference. You can join them, and you can also attend any of the meetings in person. So you can look at the drafts of what is happening and so forth. And I was just saying that to Ken the other day that if MPI happened today, the set of language bindings might have been different than what they are because it happened 25 years ago. Because the languages being used now are Python is used more. And Fortran is used less. By the way, how many of you are primarily Fortran users, or your codes are quite a few? In this class, we see that there are Fortran programmers. Our code examples are in C, however, but it's simple C. It's not difficult C, so you should be able to look at it and not terribly different from what a Fortran one will look like. And the work the exercises that we have involve just making changes to the MPI part of the code, the MPI functions, and use a different set of functions or do something in a different way. So even a C programmer should be able, a Fortran programmer should be able to do it. And I think that'll be the case tomorrow as well in the OpenMP, where Tim Matson will say that you need at least a reading familiarity with C, because even his examples are in C. And Thursday is actually more of C++. The Kokos and Raja have C++ abstraction, so that's a little more C++-ish, but I think you'll be able to follow. Okay? All right. So this chart just shows that MPI 3.1, its features are available everywhere on any system that you might run on. So that includes the open source implementations, the Cray, IBM, Intel, even the Chinese system and the Japanese systems, and some European ones out there. So there may be a few X's where some things were missing, and we don't have the very latest update on this. So what says Q2.18 and Q1.18 may have already been done. So we didn't get a latest update on this, but whatever we are covering today is available for you to use or wherever you're running. Not just on the LCF systems, but even on your home system, wherever you're at your institution. So one thing to remember is when using MPI is that all the parallelism is explicit in the sense that there is no magic happening underneath, or there's nothing that you don't know what's going on. So in one way that is good, and in another way it means that there's a little more work for you to do. That is, you have to think about how you're going to divide the data in your parallel program among the processes, and how you're going to operate on the local part, on the local data of each process. And whenever you need to communicate, that is, you need data that somebody else has, or you need a collective result, or you need to form a sum or some kind of a global you need to call MPI to do that operation. So now how you do that and how do you do it in a way that it performs well is what the tutorial is about. But you have to think in parallel. So that's a little more work than something that magically does parallelism for you. But it's also good in that you have more control, and if there's a performance issue, you are better at debugging because you know what is going on. If there's magic happening, then when it doesn't happen, then you don't know what to do. You're kind of stuck there. So that's something to keep in mind. I'm not going to go into basic MPI communication, but just one slide about semantics, just so that everybody is clear about what is a blocking operation and what is a non-blocking operation in MPI. So the basic MPI sends and receives. MPI send, MPI receive are called blocking sends and blocking receives. So what does it mean for a function to be a blocking send or receive? So on the receive side, it's clear when a blocking receive means it will not come out of the receive until it gets the data. You can that's somewhat obvious from the name. On the send side, it can be a little it's a little not entirely straightforward, or it can be a little tricky. So on the send side, the send function in a blocking send, when the function returns, what it means is the data in that buffer that you're passed to the function, the one that you're sending, that has been moved out of the buffer. That is, you, the user, are now free to either free that buffer if you don't need it, or overwrite it with something else. But the old data has been removed. That's the MPI implementation is giving you that guarantee. Now, where that data has gone, that you don't know. So it could be locally buffered on that node, which is not so common. It could be in transit. It could be somewhere on the network, or it could be have reached on the other side. You don't know. That it often depends on the size of the message. So typically, if it's a short message, by short message I mean a few kilobytes, or usually even less than a megabyte, the MPI implementation would just send it across, which is known as an eager send in MPI implementation parlance, because it knows, or it assumes that on the receiver side it will be able to store that message somewhere, even if the receive has not been called, that there will be enough memory that it could allocate, or it has allocated, to store this temporarily if the matching receive has not been called. If it's a large message, and what is small and large is up to the implementation, and the implementation may not tell you that. So you don't know. So you can't make assumptions based on whether the function will return or not. But at some point, when the implementation thinks that it's a large enough message, which could be a megabyte, it could be even less than that, it will not send the data across. It will get into a handshake mode, which is called rendezvous. So it will send a sort of a control message over to the other side, saying, I have this message to send you, with these matching parameters, which is the tag typically, and the source, of course. Are you ready to receive it? Has the receive been posted? Because once the receive is posted, the user buffer is available to put the data into. Then whenever the receiver replies with a return handshake or a control message saying, yes, there is a matching receive has been posted, then it will send the data. So there is a two-step thing happening internally. And when it gets into this two-step thing, the MPI send will not return until a matching receive has been posted on the receiver side. So that's where the send can block until the receive has been posted. So that is a blocking send and receive. The other one is a non-blocking send and receive. I send and I receive. Here, the function returns immediately. That's what the I stands for. It's an immediate send and immediate receive. What immediately means is it will not wait for any action on another process before it returns. So this MPI I send will return without, even if this I receive or the matching receive is not called on the receive side. So it's not going to deadlock or wait for some action on the other side, which means that it's a little safer to use than that, because if you call a blocking send and this other receive doesn't happen for an hour, that send could wait for an hour for that receive to be posted if it's a large message, because then the handshake will never happen until that receive happens. Whereas here, the I send will return immediately, but you cannot touch the buffer that you have passed to the MPI send function, because there's no guarantee that the data has been moved out. That data is still it could still be there. But it returns, and you could do other work after that. You could continue doing some other compute, or you could send some other messages. And sometime later, and as late as possible, when you absolutely need to know that the send has happened, that is, the data has been sent, because you need to reuse the buffer, or you need to free the buffer, or you just need to know that it has been sent. Then you call MPI wait, where that's where it can block. If this receive is never called, then at the MPI wait will not return, because then it has to wait for the for the data to go. For a long message, of course. For a short message, it might send it, but it will never get matched with anything. So the program would be in error. So similarly, on the receive side, the I receive will return immediately. It will never wait for anything message to come until sometime later you call an MPI wait, where it will not come out until the data is received. And there is another variant, instead of MPI wait, there is another function called MPI test, which is a non-blocking way of checking has this happened or not. And if it's not happened, fine, you can come back and check again. It won't block. So that's the MPI test wait. So is it clear what is the difference between? Yeah.
So for MPI send, when it's in eager send mode,
Yeah.
when am I correct in understanding that it does not match the MPI tags?
Yeah, it won't try to do any matching. When it's in eager mode, it will send the data across, assuming that even if a matching receive has not yet been posted, there is enough memory available or a buffer space available where it can be temporarily stashed away until whenever the matching receive happens, and then it will get matched with that receive and delivered. So at the end, there is always matching, because send and receive, you have to send the data to the right receive. You can't say there are rules on how the matching happens. So matching happens, but the data gets sent in any case, assuming that there is buffering available, that the implementation thinks that it's not going to consume so much memory that the application will complain about it. Yeah.
So for tags, are those really optional, or what is the advantage of tags?
Yeah, tags are they are optional. It's more for your program correctness. So if you don't use tags, then the messages will get matched in order. So when you're doing the first send gets matched with the first receive that gets posted. I mean, send always has a destination. So it's going to go to a particular rank on the other side, and there the matching will happen in order of which the sends were issued. If you can do out of order if you do the tags, so if you use specific tags and then the receives have a different specific tags, then they will get matched with those tags. But there are wildcards as well. On the receive side, you can say any tag, so it would get matched with any of these tags. So there are all these combinations available. So it's more for programmer convenience and correctness in the sense that it could get confusing if you do lots of these wildcards in a complex program. So it's more for your sanity and your understanding of the program semantics. But MPI has a well-defined semantic about how the matching. So it's not usually not random. Yeah. Okay. All right. Just you can look up these pointers to the forum, the standard MPI implementations. There are many tutorials. There's a lot of material, so there's no shortage. There are tutorial books in addition to the standard. Okay, so I want to move to an example that shows how the choice of MPI functions you use can affect performance, because it could lead to unintended synchronization in the program. So even simple operations can have some surprising behavior, because it's not just it's not just two processes communicating. There are many communicating. So there could be contention because there are so many communicating with each other that it could result in some kind of ordering of communication that you didn't expect or you didn't even intend. It just happened because of the way you wrote your program. So the example we will use for this is exchanging data on a mesh-like topology, and we have a similar example for the hands-on, which is let's say you have a 2D array which you have decomposed in both dimensions among processes, and you want to do nearest neighbor communication to exchange the boundary rows and columns. So it's this kind of communication where you have to send data to your nearest neighbors and receive the boundary elements from your nearest neighbor. So one way of writing this is you have a loop across all your neighbors, and you do call MPI send with the edge data to your left, right, bottom, and top neighbors. If you are in the middle where you have neighbors, at the edges you may not have neighbors, and then you call the receive similarly. So what is the problem with this code based on what we just covered?
Blocking the first few sends might wait till there is the receive.
Right. So you're using blocking and MPI send. So if the message is short by whatever the MPI implementation, that MPI implementation on that system considers a short message, it will go ahead and send it, and it will go to the receives, and the receives will get posted, and the program will work. But the same program on another system where it thinks that message is above the short message limit, it will block there because the send will wait for the handshake to happen, right? So it will never come out of the send because there's no receive posted. Everybody has posted the sends first. And this is still a common mistake that we see among programmers. And if you're sending large amount of data, you'll find out immediately because your program will hang, and then you'll realize it. But for short data, it'll work sometimes and not elsewhere when you run it elsewhere, and that becomes a problem. Now, a variant of this is to order it in some way and say if I have a down neighbor, then I call MPI send, and of course that is followed by the receive. And if I have an up neighbor, then call MPI receive. That is, you order it that way. So if you do that, it ends up sequentializing because who will call the receive? The one at the bottom, because the one at the bottom they don't have a down neighbor, so they don't have to call the send. They call the receive first. But then you've kind of sequentialized the process that the processes at the bottom row call the receive, and then the send gets matched, and then it's kind of the wave propagates up. Everybody's waiting in some kind of ordering imposed by this way of writing the program. Now, another way to do it is post the receives beforehand using non-blocking communication. So you do the MPI I receive, all of them for all your neighbors, but then you do your blocking sends. Now this looks somewhat harmless because you have posted all the I receives, so the sends will match. It's not that they're going to deadlock because the receives are not posted. They will match, but it tends to not perform well in practice because the send is still being a blocking send. It imposes some ordering, and we'll see with the help of a figure. So suppose we write the program where we are sending to the bottom neighbor, to the right neighbor, and to the top neighbor, and to the left in this. So in the first step, there will be these processes will send to their bottom neighbors. The ones at the last row, they don't have a bottom, so they send it right, and the one out there doesn't even have a right, so it sends it above. Now, because of contention, so if you see, this process has two other processes sending to it, and there also is a similar story. Some of these end up taking more time than others, so there is twice the time taken here. Assume that it, because of the system cannot handle two in the same time as one. So if there's contention, it takes in a simple model. Assume it takes time. It takes twice the time. So some of these will not finish in this one step, whereas the others will finish. And those who finish go ahead into their next step, whereas the ones at the bottom are still in their previous one. And if you continue this, eventually it finishes, but there is some uneven, I mean, there is some that are idle in some steps, some are taking longer than others. And, and finally, the ones in the middle who had the most communication to do their last step of sending it to the left. So if you look at the time that this takes, and this is on a somewhat older system, there's unevenness in the amount of time taken, and then the rank 1, that was the one in the middle, it took the longest to finish. And this also shows the distribution of the send timings, which are kind of all over the place. So why did it take this long? It's the ordering of the sends, the blocking sends. Assume that these are large messages. They introduce a delay when there is contention at the receiver. So when there are 2 neighbors trying to send to 1 with blocking sends, then that ends up taking twice the time than others, and others are waiting for that operation to finish and so forth. So the real fix is to call non-blocking in both, for both the receives and the sends. So here, you are not imposing any synchronization or any sequentialization from your side. The program has left it to MPI saying, this is what I want to do, and let the MPI schedule it, or let the network handle it. And since the multiple sends have been issued, no one's going to sit idle waiting for the next thing to happen, because it can go ahead and do the next send. So you can, in 4 steps, this operation could complete because of things could be done concurrently. And then the timing also shows a more even distribution. And then the ones in the middle, the ranks 5 and 6, take the longest as expected, because they have 4 neighbors to communicate with. So the message here is, from your side, you should aim to defer synchronization or avoid synchronization as much as possible. And the simple way is to use these non-blocking sends and receives and call the wait as far away as possible after the send and receive. If you call it right away, if you do an MPI I send and immediately MPI wait, that is as good as a blocking send, because there is nothing happening in between. You're stuck in that wait right away. If you can call it later, as late as possible, then you're getting more overlap, less synchronization. You're letting things happen. And another example, and another thing we'll see later, probably after the break, after the coffee break this morning, is the MPI barrier synchronization. And the MPI barrier is a collective that also synchronizes, and it's usually called for no reason. It's not required. Most often, it's not required in your program. People just put it in there to be sure, or just because they've done a lot of work and, okay, let's call a barrier here. That also unnecessarily synchronizes. And we'll get to that when we look at the collective functions. So is this part clear? It was just to get the idea across that the choice of function matters. You should know whether your function is synchronizing or not, or what are the synchronizing implications of it. Yeah.
I got a question on your example, the last
Yeah.
slide, I guess. Oh, sorry, the one with the program. Yes, does it matter if you switch the sender, I sender, I receiver?
Yeah, that's a good question. And there is, on some systems, one might perform slightly better than the other. There is no really good solution, or single answer to that. If you do this, it'll be it'll be fine. One advantage of this is if the receives are posted, then when the send is issued, the data can go straight to the user buffer on the other side. So one usually prefers this method. Yeah.
Are there scenarios where it'd be advantageous to use a blocking send?
Not advantageous, but in some cases it may be no different than using a non-blocking send. So if you're doing a very simple pairwise communication between 2 processes, where if you did a non-blocking, you would almost immediately call the wait because you needed to know at that point itself. Then you could as well do an MPI send. But otherwise, Otherwise, no real reason to use an MPI send. So if you can replace the send with the I send wait combination, where the wait is somewhere further below in your code, not right away after the send, that your code allows you to do that. I mean, the semantics of your code, or then it's always better to do that kind of thing. Or if it's a very short message, then if you're just sending a single integer or something, then the MPI send also can just send it across, and that should be okay. It's when you're dealing with larger data where this is a problem. Okay? Oh, yeah.
Will there be a discussion on profiling tools or debugging tools for these types of?
Yes, so there's a whole day dedicated to tools. That's next Monday, I think, and there they will cover these kinds of tools. And we have some material that if we have time, we could cover, and or we could talk in the break, or we could talk after dinner or so forth. So Ken has some material about debugging and profiling, but we thought we didn't want to cover it in this because there's a whole day on. There are experts who develop tools who are coming on. I think it's on Monday next week that they're going to present that. And there are good tools available nowadays too. Like the Tau tool from Oregon is there, and there is Scalable, and there are others, and the vendors also have their own tools. So Intel will have something, and Cray will have something. Okay. Okay, I think we're doing good on time. Let's cover MPI derived data types, and then we will get to the hands-on, and I think we'll be able to start the hands-on just before the break, and we'll see how that goes. So in MPI, there's something called a data type that's a parameter to every function. MPI send or receive will have a buff count data type, and then the destination tag and whatever. In most programs, you will just use the data type as the type of data that you're sending. So it'll be an MPI int or MPI double or whatever. But there is also something called a derived data type that you can construct, and that is used to specify a non-contiguous data layout that you can communicate with a single function. So let's say you have a 2D array, and that is a C array, so it is row major, but you want to send a column of the array to some other process. So that column is not contiguous in memory. So you would either have to copy it. One way is to copy it contiguous and then send it across. Of course, one way is to send one element at a time, which is terrible because that's the latency is high. So many people would copy it into a buffer and send it and unpack it on the other side. But MPI allows you to use one function and specify this strided data. You can use a vector type for that because it's a nice uniform stride. And MPI will do it, or at least can do it nicely, efficiently for you, and copy it directly onto the buffer on the other side. And that's where derived data types come in. They are defined. There are several types of derived data types. The most general one is there is one that is the most general, where you can define any arbitrary non-contiguous layout in any complex layout. Of course, that is more difficult for the MPI implementation to tune or to optimize. But there are others that are more structured, like the vector type and a few others, which the implementation can understand quickly and do something better. So let's look at this. I'm going to skip this slide. So there are a series of functions, about 4 or 5 of them. There aren't too many for constructing data types. From the simplest to the general. So the first one is to define a contiguous type. It's called MPI type contiguous, where you pass a count, the old type, and the output. The function will return a new data type, which is the count, effectively. A count number of old types together is one type. So if you pass how much is this? This is 7. If you pass 7 and MPI type as, say, MPI int, if these are integers, the output would be a data type that represents 7 integers. So the output, it's an opaque object. It's not something that you can understand, the handle that you get back. But to MPI, it will treat that as a unit of 7 integers that can be treated as 1 if you use it in a send or receive. Now, in a send or receive, you don't need to use type contiguous really, because the buff count data type allows you to send 7 integers by saying count equal to 7 and then integer. So typically, this is not used in simple sends and receives because you can do it without that. This tends to get used if you are constructing more complex types where you need to create a contiguous and then do something else in addition. So it tends to get used less than the other ones. The one that gets used more often is MPI type vector, where there's a nice uniform stride among the data elements, like when you're sending a column of a row major array. There is a nice stride of the size of the row, uniform stride. Or similarly, the Fortran array, if you're sending a row when it's column major ordering, that row is not contiguous, but it has a nice stride. So yeah, might be good to use the pointer here. Yeah, so the MPI type vector, you pass in the count as the number of elements. So if you want to, for the example where you're sending a column of a row major array, the count would be the number of rows. That's the size of your column. Assume that the block length is 1. If you're sending one unit at a time, one data element, one contiguous element at a time, then it's 1 in that case. But if you had something like this where there is blocks of 2 elements, then you could send count equal to 2. Then the stride is the gap between the two. And then you pass the old type, which could be a basic type. Of course, it could be a derived data type because you can feed the output of these functions to other functions, so you can create complex type like that. But in the simple case, the old type would be the basic type in the program, and the output would be a new vector type, which if you pass to an MPI send function, it would send the strided data without the gaps. And this is only on the send, on the side where it's being passed. Now, if you're going to call an MPI receive on the other side, that has its own data type. And there you could either receive it contiguously if you have a contiguous buffer, or you have to create your own type on the other side as well, because this type doesn't get, the data type doesn't get sent there, only the data gets sent there. So, but it doesn't mean that you have to follow the same layout on the other side. You have to only the basic type needs to match. So if you're sending data that is a integer here, on the other side, it has to be, the basic type needs to be an integer. You could have created a derived data type of a vector with a different stride or whatever, but basically of integers. If you use something else, then that is considered erroneous. And now there are other ones. Oh, this got a little out of order. Okay, this should have been first. Where if your stride is not uniform, then that can be specified with an array. So here we have a non-uniform stride. There is a gap of 3 here, 1 here, again 3 and so forth. So for that, you cannot have a single parameter. You need an array of displacements. So you actually pass the strides as a displacement. So it becomes more general. That's called the MPI indexed block. Then there is something called MPI indexed, where even the block lengths are not uniform. So instead of all of these being 2, here now you have 1, then 2, and so forth. So now there's an array of this as well. So this is another one. And the one slide that got out of, oh no, it was correct. I was confused. Sorry. So there is another one called MPI for vector or even for indexed, where there is an H version, MPI H vector, where the stride is defined in bytes instead of units of old type. So it's just a detail that in MPI type vector, this stride is specified as the number of data types. So here it would be stride would be 3. If you're doing MPI H vector, then the size would be 3 into size of int or 3 into size of double or so forth. So it's just a generalization of that. And then similarly for indexed, there is an H version of it where the stride is specified in bytes instead of old type. Then the most general type is an MPI type struct, where Not only you have different strides and different displacements, but even the data types can be different. So if you're like a C structure where you have different types in there, you can use an MPI type struct to create that data type and then send that struct across, or an array of structs across. And there are a couple of convenience functions, which I won't get into details, where if you want to send a subarray of an array, let's say you have a 3-dimensional or 4-dimensional array, and you want to send a sub-array of that, it's difficult to create that data type on your own because the non-contiguous layout gets a little tricky. So there are convenience functions where you can specify that in terms of array coordinates, the array indices of that subarray. And MPI will effectively create that the strided data type for that. And there's one more for a distributed array. And then there are a couple of other functions. When you create a data type, you have to also call MPI type commit before you can use it. So you can create an MPI vector type and then call MPI type commit. And at that point, in this MPI commit function is where the MPI implementation tries to understand the data type that you have created and store an internal representation that it can use during the communication so that the communication happens efficiently. And you can call these data type functions recursively to describe some complex layout. So you could start with an MPI vector and then use an MPI indexed after that or whatever. At the end of all that, if you need to, that is, you call commit once, and that's where MPI tries to understand what you've done, what you're trying to express, save an internal representation that it can use for doing the communication efficiently. Now for simple types, it's easy. For a vector type, there's a nice uniform stride. MPI can do it easily. For the most general case, if you do a struct or some weird, it typically will not be able to optimize it. It will just store lists of addresses and lengths or something like that, and just copy it into a buffer, and so it'll do what you would do by creating mem copies for the most complex types. For indexed or vector, it can do better because the hardware now supports strided communication. So the network hardware, you can point it at addresses on one side and also addresses on the other side, and the data can go in a non-contiguous. So to the extent that that can happen in hardware, then MPI will try to do it. Otherwise, it will do the best it can. So in practice, historically, derived data types have not performed well because the implementations have been slow to tune it or optimize that feature. But there have been papers and research work on how to optimize data type, and it has made its way into implementations. So you should find better performance now. Another use for data types is in the parallel I/O part of MPI, where you could have a file containing a global data structure, like a 3-dimensional array, and you want to read a subarray of it. Each process needs a different part of that. So that becomes a reading like a subarray out of a big array. So their data types get used again, derived data types. So that's a common use case in the I/O part. Okay, so our next we're getting into the code example now. Any questions so far before Yanfei explains the code and we do an exercise?
Yes, I have a question concerning the different implementations of the MPI standard.
Yeah.
Are there detailed benchmarks of performances in a variety of situations?
I mean, comparing implementations?
Yeah.
Yeah, I know over the years, there might be here and there, but things change so much. Everyone comes up with a new release in 3 months or 6 months. It doesn't. So right now, today, if I don't think you'll know which one is better than the other. But in general, if you're running on a supercomputing system, use that vendor's implementation that is provided there. If you are running on a managed cluster where there is a system administrator and it's a resource provided by your institution, typically there will be a primary implementation that they'll point you at saying use this as the first one. And there might be a secondary one as well, which you just need to use the right path to access that. Often there is more than one implementation on a system, and if one doesn't perform well, you can, for some particular function, you can switch to the other. And it always report any problems to the implementers because they will. That's how they will fix that. And that's how we also tend to fix things. But yeah, there isn't a, things change so frequently that there isn't a good data set for that. Yeah.
Is for complex data structures and performance-wise, what it would be better to use MPI pack and unpack, or actually?
Yeah, there's MPI pack and unpack. That's another function where you can pass a data type and it'll pack it for you. You could do that if you think you can pack it manually yourself, and if it's really complex because you know what it is. That might, in practice, that might be better, because I think MPI pack would also tend to not understand the most complex type. I mean, in terms of doing it efficiently. I don't know. Do you guys have any different data for complex layouts? Would you still recommend data types, or?
I mean, we always recommend using MPI, but as Rajeev said, the implementations don't necessarily perform well for all cases, and so it's likely for very complex layouts you will do better than MPI can do, just because MPI is kind of hamstrung by the generality of its interface. It has to be able to handle very complex recursive data types, and so even if your data type is already complex, you probably know more about it than MPI does. So,
and for example, the data type that is for structures, it cannot work with dynamic arrays. For example, if I have a C struct with a dynamic array in it, the derived type will not work.
No, there is a general type where you can pass addresses, and you can describe pretty much anything. So, in terms of describing, you should be able to describe it, if I'm understanding your question correctly.
If it has a variable length array inside the struct, yeah, I don't know if that would work.
For that case, I would have to go for MPI pack.
Probably.
No, but if MPI pack works, the data type should work. It's either manual packing or, because for MPI pack you need a data type, right?
Yeah, this is probably good for a side discussion.
Yeah, I personally don't use MPI pack that much, because MPI pack goes through the same logic internally as the data type engine would, MPI data type engine would, because it's using the data type there for packing. So you would either, the reason MPI pack and unpack are there are mainly historical. When MPI was defined, the other libraries that existed had these kind of pack unpack functions, so the people wanted them at that time. The actual pack. If the user does their own packing, that can be done more efficiently. Of course, it takes more effort from the user, but the user knows what it's not trying to reverse engineer or understand through the data type interface. So I think the choice is either use the MPI derived data types in communication, or do the manual packing yourself. I think your manual packing might be more efficient than the MPI packs packing, I think. Okay, so Yanfei is going to explain the code example, and then we'll do our first, the first hands-on.
So I just want to make sure everyone has the code example. This is the link to a box folder where you can download a pack of code, or if you're on ALCF machines, this is a project directory where you can look at all the codes, and I would just recommend you copy this entire directory to your home directory, so you have all the codes and JavaScript for running it on Coolie. Okay, and if you have MPIG, you can run all the example on your own computer. That's no problem. So the code we're looking at, it should be in this non-blocking P2P directory. This stencil. Okay. If you can't access Coolie, just go to that link and download to your local machine. Because for this step, I'm just going to walk you through a little bit what the code is doing and what the basic structures and what are you expected to change during the course of the tutorial today. Okay, so let's just I'll just talk about it. So the code example that we use for the entire tutorial is a 5D stencil, which is a very common kernel in many of the scientific computing applications. So in our situation, we have a 2D. We have a global data structure of a 2D mesh representing. You can think as a metal plate, okay? And the problem that we have in this example code is we have 3 heat source that's in fixed position on this plate, and in each iteration of simulation, we just keep pumping a fixed amount of heat into it, and the heat will dissipate on the plate. So at the end of the execution, we're supposed to get what is the total heat of that is accumulated on the entire plate. Okay. So that's the global structure. And is there anyone doesn't know what a 5D stencil is? Okay. Oh yeah, 2D 5-point stencil. 2D 5-point stencil. Okay, no one. That's good. That's good. Okay, so as you may or may not already know that for us to parallelize the problem, we have to first decompose the global data structure so the data can be distributed into each individual MPI processes, and they can be calculated and updated locally. And all this process need to do is exchange some boundary data, which we'll see in the next slides. So I roughly divide the example code, the stencil.c, into 4 big steps. So the first step is, as I mentioned, is the domain decomposition. Essentially, is we divide the global grid into some subblocks, and for each of the MPI process, they need to figure out where am I as an MPI project process in this, for example, this 3x3 process grid. Okay, and second thing is you need to figure out what is my local block position in relatively to the global data block position. Essentially, assuming this is a row major, so going this direction, and essentially for each process, you need to figure out what is the coordinate of this piece of data. What is the coordinates? It's coordinated in the global grid, and because in local grid it's always 0, 0, right? But in global grid that will be an offset, which I will show you later in the code. And I also need to figure out what are my neighbor processes rank. Okay, so in this case it is 1, 3, 5, and 7. Okay. Okay, and for all the boundary processes, we use MPI proc_null as the neighbor that does not exist. Okay. So that brings after that decomposition, we have to figure out what are the necessary data transfer. So for 5D for 5-point stencil, essentially we calculate each point based on the value of itself and 4 neighbor points. So the problem happens when you are trying to update your local data on the boundary of your local block, where you have one piece of data that is you don't have locally, which is belong to your neighbor. Okay, yeah, that piece. So what happens is we create a data structure called halo region. Essentially, is the yellow part here. Okay, these are your local copy of the boundary data that your neighbor has. Okay, so essentially, if you go back to this one, that yellow region is supposed to be wrap around your local block. This is the data you own, and that yellow one should be the data that you need but doesn't own by you. That's your neighbor has it, and you have to do communication to get those data. So in our example, we have some names for, so BXBY is describing the size of the data you own, your local block. So then you can easily figure out that for your calculation, you need to actually allocate a BX plus 2 by BY plus 2 array for all the data in your own data and the halo. And the four corners are not necessary in this scenario, in this example. And we have a function that I can show you later for that, doing all the allocation and adding the communication buffers for that. So after having all those data structure ready, the calculation essentially becomes we have two for each piece of this subarray. We have two versions. There's old and new. So essentially, you calculate in the new based on the value in the old, and then after in each iteration, the matrix alternates. So the new becomes the old, and then you updating the new. So it's do a buffer. Okay. So the third step, which is the most important part that in our tutorial, that is the communication. So in the non-blocking P2P version, we're using non-blocking point-to-point communication to do the data exchange. So data exchange essentially is for each process, you need to send the boundary data that you own, which is the green cells here, to your neighbors, and also receive your neighbor's boundary into the halo region, which is the yellow region, and it will happen like this, okay? And after that, because the data you own is the latest, and the halo region is the latest, then you can proceed with the calculation. And let's do that again. So you're sending your boundary to your neighbors and receiving your neighbor's boundary into a local region. Okay. In this particular example, in the P2P version, we have, instead of sending directly to the matrix that you're doing the calculation, we have a dedicated send-receive buffer for this purpose, because the column data is not contiguous. We do some manual pack-on-pack for that. And for the cleanness, we also did the cleanness and symmetrical for the code. So we also do the packing-on-packing for the raw data, which is not absolutely necessary. Okay. So the last thing is just there's an MPI already was called to just calculating how much heat is available on the board. Okay, so let's look at the code. Okay, so here, if you go to the stencil.c around line 90, this is where the domain decomposition is happening. Okay, we have so here are some variables. PXPY are the so the PXPY in this example is the dimension of the process grid. So if we're running on Cooley where we can only run 12 processes per node, this will be something like 3x4 or 2x6. Okay, and then the RXRY is the coordinates of the current process in this global process grid. So that's why you see that it's using your local rank and calculating this. And then for the neighbors, it's pretty straightforward just to figure out am I where because I know my coordinates, then I can calculate what my neighbor is. Okay, and then the last thing is figuring out the block size. The n is the dimension of the global data structure, which is n by n. It's a square. So you have to in this example I will use 120. So you basically divide that using px and py. Then you get your dimension of your local block, and also you figuring out the offset, which is the top left top left corner cell. It's coordinated in the global data structure. So after that, we're calling the init sources function here, which is just initialize the data and figuring out whether the code has a heat source in this local process. But the data location, the buffer location happens in here in this alloc buffers function, where we allocated two metrics for the local data, and we have send buffer and receive buffer for 4 neighbors. So totally 8 buffers. You can just look into the function, but I'm going to skip here. So after that is the most exciting part, which is the communication. Okay, so because we're doing 4 send and doing 4 receive for each iteration, so we created 8 requests, and before doing any send and receive, we pack the data into from our matrix to the send buffer, and then we issue in the send and receives, and then we wait for all these 8 requests to complete, and then we unpack the receive the data in the receive buffer back into the halo region of the AO, and then we in the update grid function, it will do the calculation, and then it will just swap the AO and A new and proceed to the next iteration. Okay, and when all that is done, there's a step for the R-reduce, figuring out the total heat and then print out. And if you look at the topmost directory of the example, you should see a file called sample output. That is the output that you will see if you run with the configuration in the submit.sh file, which set the global grid to 100 by 100, 120 by 120, and then the heat is 10 and running 1,000 iterations. That is the expected output. The heat will always be that. The execution time depends on the code. Okay. So that's the structure of the base version. This is the start point of the next of the hands-on that is we're going to do right now. Okay. Does anyone have any questions about this? No? Good. Okay. So the first hands-on with that we're going to do today is derive the data type. Okay. So as I mentioned in the base version, we use dedicated send and receive buffer for communication because the column data, especially the east-west boundary, are not contiguous in our memory. So we can either choose send these data one by one, or in our example, we have to create a contiguous send and receive buffer and unpacking to from it. So the problem with this design is the overhead of all this memory movement. This is memory copying data is kind of expensive compared to other stuff, and you're not contributing any scientific stuff in there. Okay, so the idea is since we have derived the data type and we can create a vector type for the column, so the MPI library can essentially take over the transmission of the non-contiguous data. So the exercise that we are going to do is, on top of this, you need to modify the P2P version into a version that uses derived data type. Okay, so you need to derive the data type for the columns, and if you want, you can also create for the rows if you use MPI type contiguous. And then you should be able to do send and receive directly from AO and A new for the communication rather than doing pack on pack. So essentially, if you're looking at the code, basically your changes will be roughly, most of them will be in here, but you need to allocate the data type before that, before the iteration. Don't do that in each iteration. That doesn't make sense. Pre-allocate your data type, and that's good for the entire program. Okay, and then you need to change the communication here without using these send receive buffers. Okay, just use AO for communication directly. And that's what we are going to do for the first hands-on example. And we have about 10 minutes. That probably, I'm not sure if that's enough, but we can, if you want, you can, because we have break after this, you can keep doing this in the break, and we can continue. And if you have any questions, you can just ask.
Yeah.
So
We have some time till the break. You can, if you like, you can continue in the break. There are other hands-on during the day, and there's whatever you don't finish, there's time after dinner as well. So there'll be time for hands-on. I'll also mention that the solution is available in that, and the last bullet tells you where the solution is available. But just hold off on looking at it. Try doing it yourself first, and if you absolutely cannot, or if your code seg faults or doesn't give the right answer, then look at the solution. And for all of them, the solutions are there, and we even tell you where they are, but try doing it yourself first. And if you have any questions, just call one of us and we can help you. I think easiest would be if you have MPI on your laptop, that would be easiest. Otherwise, use any of Cooley or Theta. Or if you have your own system at your institution and you can easily do it there, feel free to. So do it anywhere. In this session, let's quickly look at collectives and non-blocking collectives, followed by another hands-on for a short period. And then Ken will begin with RMA, which we might continue after lunch if we don't finish. So you probably already used collective functions, so I'm not going to spend too much time on them, but they're important in MPI because they encapsulate commonly needed communication patterns, and they do it in a very optimized way. So if you want to broadcast some data to everyone, or if you want to do a reduction operation, that is to find the sum of all elements across processes, or scatter or gather, which are commonly needed. MPI provides functions for these, and they're very heavily tuned in implementations. There's a lot of research on how to tune these communication operations, and the implementations have actually adopted a lot of these. Vendors spend a lot of effort in tuning them. And often in the code, in the MPI implementation, there are many algorithms in there for things like a broadcast. It's not just one algorithm. So depending on your size of message and the number of processes, it might switch between algorithms. On different systems, it might use different things. Some networks and systems have hardware support, so that gets used. So there's a lot of value in using these. And what does a collective function mean in MPI? The collective means every process in the communicator, that is the first parameter typically of this function, there is a communicator is the parameter. Every process must call this function. If one of the processes doesn't call it, then everyone might wait for that process to call, and the program will hang there. So if you're using MPI COM world as your communicator and you call a MPI whatever broadcast, that means all processes in COM world should call it, and it has to be called in the same order. So if you're calling a broadcast, reduce, or whatever, you can't mix them on different processes. They have to be called in the same order, otherwise it is user error. And that's why there are no tags in these collective communication functions, because they have to be matched in order. Non-blocking collectives were introduced in MPI 3, and we'll look at them. So you can do a non-blocking broadcast or non-blocking reduced. And there are three types of collective operations. There is synchronization. There are ones that do data movement, and there are ones that do some computation in addition to the data movement, which are called reduction function. So for synchronization, there is one function called MPI barrier. And the way MPI barrier is defined is that what it says is that all processes that are part of that communicator pass to barrier, no process will exit the barrier until everyone has reached that barrier or called that barrier. Okay, so that's the semantic of a barrier. Nobody can get out of the barrier until everyone has called the barrier, has reached the barrier. So if one process is stuck somewhere else doing something else, everybody will wait until they reach that barrier is called. So that's how there is a barrier synchronization. However, note that this is also true that a barrier is rarely really needed in a message passing program. It is used more in shared memory when you're trying to coordinate timing of accesses or something. But in an MPI program, there are only a few cases where you might need it. So one place where you might need a barrier is if you're doing some timing or performance measurement in your program. It's common to start all processes at the same time, just so that you're measuring the parallel performance. So you call an MPI barrier, and then you start the timer with MPI W time, and then you do whatever operations you want to time. And at the end, everyone calls MPI W time again. So you have the start time and end time. You calculate the difference, and then you do a maximum among all processes. So you find the time taken by the one that took the most time among all. So you start them at a common point, and a barrier is a good way to do that. But otherwise, if you're running your program for a scientific result, you're running in production, you're not actually measuring the performance, you don't even need that first barrier or a barrier anywhere else in your program. There is one case in the one-sided communication in one particular form of synchronization where a barrier may be needed. We can talk about that later. That's one use case. But otherwise, there is no real common use case. But on the other hand, in apps, you might find barriers in the code without any good justification. So one thing you could do is look into your code and see where there is an MPI barrier, search for it, and then ask, is it really needed here? If you're debugging, that's fine. You need to do whatever method to get rid of the bug. But otherwise, it's not needed because you're unnecessarily synchronizing. Again, yeah.
So I think in PyTorch, using MPI as a backend, their data parallel, they use the barrier quite a lot, right?
Okay, I've not looked at the PyTorch backend.
Data parallel, like
yeah.
They deep learning model in
yeah.
each GPU, and then they want to do the barrier data fetch, and then after the gradient update, they barrier again. Is that kind of use case of barrier?
Kind of comment on that. So
yeah.
I've used the same package, and the justification apparently there is, if you're training on hundreds of GPUs, some of the GPUs will learn it first and saturate the rest of the process. So they added as a way to make sure that it's synchronized parallel gradient descent. I think that's the only, and it kind of makes sense, but I think it's not performant, but at least you know that the training is not affected by the GPU latency and rather by your hyperparameters. Because that's what I understood when I used it.
Yeah, just think maybe
yeah.
that's the use case.
So maybe they're doing it for some performance reasons or some other reasons specific to that. So if you think about your code and you can justify to yourself a need for a barrier, and that's fine. But if it's just in there because you think it's a good time to have, you've done a lot of work in your parallel program, okay, let's put a barrier in there, or you're not sure, so you throw a barrier, or a barrier gives you the right result for some reason, then there's something else going on. So in the normal scientific codes, I would question whether a barrier is needed, and it might be needed, but think about it and see if you can remove it, or at least comment it out when you're running it in production. So the next set are the data movement functions. So there's a broadcast where there's a root process that can broadcast a value to all other processes in the communicator. The root doesn't have to be rank 0. You can have any rank. You specify the rank of the root? It could be anything. Then there are scatter and gather operations. So the scatter operation is where you have an array and you want to scatter it. You want to send parts of it to other process. So the first part goes to rank 0, the second to rank 1, and so forth. That's a scatter. And then again, the root of the scatter could be anything, doesn't have to be rank 0. Then the reverse is the gather, where everyone contributes something, and that gets sort of appended or concatenated into a bigger array at the root, which again could be any rank, not 0. Then there are the all variants of these functions, all gather and all. There isn't any all scatter, there's an all to all. So what the all gather does is that it's like a gather, but everybody gets the result. So the result is not just at the root, but everyone gets it. And internally, it's implemented in some efficient way. One way to implement it would be to do a gather and then a broadcast, right? You gather to a root and then broadcast from the root, and everybody gets the result. That's not the most efficient. There are better algorithms, and internally, the MPI would do it better than that. Then the most general form of communication is all-to-all, where each process has a distinct data item to send to every other process. So the difference between all gather and this is all gather is everyone gets the same result. So it's not distinct, it's not unique items to each process. So all gather is easier to implement because internally you can do some things because the data it's the same result that goes to everybody. Whereas here, everyone's getting a unique piece from every other process. That's the hardest to implement, hardest to optimize. So avoid using the all-to-all unless you have no choice. I mean, if you have this kind of communication pattern where everybody gets something distinct, then all-to-all is the best you can do, but it's harder to implement. Now, again, what are the synchronization semantics in these functions? So in does not mean synchronizing. There's a difference between collective and synchronizing in the sense that in a broadcast, for example, when the root has data that needs to go to everybody, the root may send, depending on the algorithm used, the root may send that data to other processes without the other having even reached their broadcast. Particularly if it's a small, if it's a single integer or some small data, it doesn't even need to wait for others because it knows that internally that can be buffered. Whenever the broadcast gets called at the other side, it will get the data. So the broadcast is not a synchronizing function. When one process exits from a broadcast, you don't know whether others have reached the broadcast yet or not. They may be somewhere above. Similarly, scatter and gather are also not synchronizing. Of course, they are, the scatter cannot happen until the root calls the scatter because the root has the data. Others are not going to get the data unless the root has called the scatter. Similarly, on the gather side, the root will not exit from the gather unless everybody has called gather because it's getting data from everybody. So everyone has to. But for the other processes, the non-root ranks, they don't, whenever they get their data, they are done. So for example, when 0 sends A to, not A, let's take B. 0 sends B to the second rank. The second rank can exit and go on with the computation. The others may not have even reached the scatter. So broadcast, gather, scatter are not synchronizing. The all versions are synchronizing because everyone needs data that everyone else has to contribute. So there's no way a process can get out unless everyone else has called that collective. So in an all gather, there's no way any rank can get out because everybody needs the whole, the whole set that everyone else is contributing. So the all versions, they are naturally synchronizing. There is effectively a barrier like semantics. There's no barrier called there, but no one can get out of an all gather unless everyone has reached the all gather. And similarly, nobody can get out of an all to all unless everyone has reached the all to all. So these are the internal semantics of is that clear? The difference between collective and synchronizing. Collective just means that everyone has to call this function at some time, and the ordering has to be maintained. You can't call some other collective in a random order. They have to be called in order. When they get out of that collective is where the synchronizing aspect comes in. And by the definition of the operation, some are synchronizing, some are not synchronizing. Okay? Then there are collectives that do some computation in addition to collective communication, and these are the reduction operations. If you want to form a sum across, you want the sum of a value across all processes, or you want the minimum, maximum, or a whole variety of operations, you can call reduce. There is also an MPI all reduce where everybody gets the result. So the normal reduce is the root gets the result. All reduce, everybody gets the result. Again, all reduce becomes synchronizing because anything with the all means everyone is getting a result that everybody is contributing to. Then there's another operation called scan where the reduction is like a partial operation from data contributed by ranks prior to you. So the rank 1 will get the result of rank 0 and 1, and rank 2 will get the result from the operations of data from rank 0, 1, and 2, and so forth. So it's like a scan. It's also called parallel prefix. So there are some parallel algorithms that use a scan operation, and that's why that's there. So this is the whole set of, or most of the collectives. There are V versions, the ones with V at the end, which stands for vector. So MPI scatter V is like a vector scatter where the data is it's not a what should I say, a constant amount of data, fixed amount of data that goes to everyone. Everyone has a different amount of data, so there is another vector specifying how much each rank should get. So it's a non-uniform scatter. So that's V. And there are also another version which is W in all to all, where even the data types can be different. So that's the most general. And for the reduction operations, you can use, there are some built-in functions that MPI provides, which are commonly used operations, min, max, there are logical or logical and whatnot, sum. Or you can define your own collectives. So you can define your own reduction. So there is a way to construct a mathematical function that gets used as part of the reduction. I won't get into the details. And then you pass this to the MPI reduce, and it will use that function. And there are use cases for that as well. Now, MPI 3 defined non-blocking versions of these collectives. So until MPI 3, everything was a blocking collective. Now, the non-blocking follows similar semantics as the point-to-point, and they're called also similar. They have the MPI_I name in the function. So an MPI_I barrier or an MPI_I bcast, which is the non-blocking. So the reasons for that are, again, you avoid the potential for deadlocks because the non-blocking is a little safer from that in a complex program. There is potential to overlap communication with computation. So if different processes are doing different things, then if you issue the non-blocking collective, you can do other work in your program while the collective happens in the background. So the semantics are similar to point-to-point. It's similar to the I sense, and the same test and wait functions, and the same request object. So MPI I send returns a request object that you pass to a test or wait function where you test or wait on, and the non-blocking collectives also have a request object. So for example, an MPI I bcast has the same parameters and then the request. The semantics are the function will return immediately. It will not wait for the bcast to be called at any other process. There's no guarantee when the broadcast operation happens. So the MPI doesn't specify that the implementation is doing the broadcast in the background. That's a quality of implementation issue. It could well happen at the wait function. So when the user calls wait, that's one place where the entire broadcast could take place. Typically, it won't happen that way. There will be things happening in the background, or it could happen while some other MPI function is called, because when you call an MPI function, the implementation doesn't just do that operation. There could be other pending communications that are still in flight that it will try to make progress on. So there's a lot happening under the covers. And they could complete in any order. So if you mix a small broadcast with a large broadcast, and again a small, they could complete in any order. The larger one may complete later when you try to test or wait. MPI cancel is not supported, and the MPI has a function called MPI cancel, where you can cancel a non-blocking send or a non-blocking receive. The implementers don't like that function because it's hard to implement, to cancel a send that has occurred. Canceling receives is a little easier if the receive has not happened, the communication has not happened. Luckily, MPI cancel cannot be used for a collective, non-blocking collective function. Okay. Now, there is a non-blocking barrier, and there are non-blocking versions of everything I said. So it's not so intuitive what is a non-blocking barrier, because as I said, a barrier is meant to synchronize, and when a process comes out of a barrier, that process knows that everyone else has reached the barrier. So what is a non-blocking barrier? So in the literature, there is the concept of a non-blocking barrier, outside of MPI, and there are other programming models that have had a non-blocking barrier. So UPC, for example, the Unified Parallel C, it's a programming model that from UC Berkeley and other places, that has always had a non-blocking barrier, where the barrier is split into two phases effectively. The first call is just like a notification. That notification says, I have reached the barrier. And then you can, that's not the point where you check where others have reached the barrier. It's to notify others that you have reached the barrier. And then the second phase, or the completion of it, is where you wait for others to reach the barrier. So you have split the barrier into two, like a notify and the wait. So in MPI, that's the I barrier, which is effectively the notification, notifying others. And whenever you call the wait, is where the barrier is actually happening in some sense. That is, and the idea is that if others have reached the barrier sometime in the middle, then the wait just returns quickly. So you're not spend time. In the time that you would just block on the barrier, waiting for others, you could do other work if your program allowed it, if the logic in your program allowed it, and that's the purpose of it. I haven't seen too many use cases, though, of a non-blocking barrier in MPI programs. There is one. There's a paper by Torsten Höfler and others on a communication pattern called a dynamic sparse data exchange, where there is a sparse communication that changes every iteration. And there are many ways to implement that, but they've used the non-blocking barrier as an efficient implementation of that. So that was one use case. I've not seen too many others, though, frankly. Okay. Any questions so far? Because we are coming to the end of this section. So is this a Ken? Do you think we should do the example now, or do you want to start with RMA?
Start with RMA, yeah.
And we come back to this. So there is an example that we have. I'll just tell you about it. We can come back to it later, or we can do it in the evening, where you, instead of doing the nearest neighbor communication to the top-down east-west neighbors using I sends and I receives, you can use a collective operation, which in this case would be, one way to do it is using an all-to-all V function. So all-to-all is meant for communicating with everybody. This is a small set of processes you're communicating with. So you use the V version of the all-to-all, where you actually specify, many of those things can be zero. So you're not, for all other processes, there is no communication, only with the one that you're communicating with. But I think let's move on to RMA and then come back to this as we see. Yeah.
Okay, so so far we've mainly been talking about MPI from a point-to-point send-receive perspective. So I'm going to present a little more on what we call one-sided communication, or RMA, in MPI. And so this is almost like an entirely different programming model. It's a different way of moving data, and we'll cover reasons why you might want to use one-sided communication as opposed to two-sided, and just give you a general overview of how it works. So one-sided communication. The basic idea here is that we're decoupling data movement from process synchronization, like what occurs in And so how does this work? So one of the analogies we use in our MPI tutorials when we're talking about point-to-point communication is it's kind of like an email exchange. Every process kind of has its own private email box, and they send messages to and from each other's email boxes so that they receive that data and they know what to do with it. When we're talking about one-sided communication, we use a different analogy in that it's more like every process is contributing to some global whiteboard where they can kind of read and write messages to each other on this whiteboard, and other processes can kind of go and see what's going on that whiteboard. And so the way they do this is each process, they have this private memory. Think about it like like I said in the previous analogy, like its email box. But what each process can do is expose part of its private memory to other processes. In this diagram, this is the remotely accessible memory portions here that each process is exposing. And other processes can then read and write directly to this remotely accessible memory, which is part of what we call the global address space, or it's like this conceptual whiteboard. And so just a diagram, and I used a similar diagram yesterday in the interconnects talk, just kind of comparing and contrasting the two communication models. And again, on the two-sided example, we have the target process here on the right who's generating some receive request, which then goes into the network queue. On the process on the left here, we're generating some sort of send request, and the MPI implementations are taking the data out of memory, matching the data on the target side with the receive request, and putting it directly into the target process's memory. In a one-sided communication example, this is all happening on the origin side. The send request is being issued to the MPI implementation. It gets the data out of memory and writes it directly into the target memory on the receive side. There's no involvement. There's no separate receive request or any involvement on the target side in this case. So why is this important? What are the possible advantages of one-sided and two-sided programming? So just a simple example here. On the top half, we have a two-sided send and receive, where process 0 in this case wants to send some data to process 1, but process 1 is delayed for some reason. And in this case, maybe the data is too big to be sent eagerly, so process 0 is just blocking, waiting for process 1 to be ready to receive the data. In a one-sided example, process 0 wants to send data, wants to write some data into process 1's memory. And in this case, process 1 might be delayed. It's doing something, but it doesn't matter. The process 1 can issue that that RMA write or RMA read, and it's not affected by the delay in process 1. It doesn't have to wait for it to be ready to receive the data. Obviously, there's some synchronization involved in making sure the right data is exposed, but if there is some processing delay, it won't affect the one-sided communication happening in process 0. So in this section, we're going to cover some of the important parts of RMA. This is not going to be we have some code examples where you can get your hands dirty with the syntax, but we're going to focus mainly on concepts of MPI RMA, and those are how do you create remotely accessible memory from within your MPI program? How do you read, write, and update that remote memory? What are your synchronization? How do you synchronize the data? And same memory model, though I think those slides are hidden in the current presentation. We can cover that if we have extra time, but I think it's not that important for you guys to know that at this point. Okay, so creating public memory, first step. Any memory in your MPI program by default is only locally accessible. So the example, if you were to just allocate a buffer X that's 100 bytes, that would be part of your program's private memory. Once the memory has been allocated, though, the user, to make it remotely accessible, you have to make an explicit MPI call that will declare that region remotely accessible. What the MPI terminology for these remotely accessible regions are is a window. And windows are a collective object. They are created collectively. So Rajeev just told us about blocking and non-blocking collective operations. Window creation in MPI is also a collective operation. So once we declare this memory region as remotely accessible, all processes that are participating in the window, and we'll see the function signatures in the next few slides, but the processes that participate in a window are derived from, you have to supply a communicator to create a window. So the processes that are part of the communicator are then part of the RMA window. Once the region is declared, processes can then read and write data to this memory, again, without the explicit synchronization I showed in kind of the diagrams on the last few slides. Right, so then in this case, we're gonna take you through in the next few slides creating a window across, in this example is 4 processes. They're exposing some part of their private memory. So window creation models. Oh, there it is. Okay, we have 4 models in MPI to allow you to create remotely accessible memory. The first one being MPI Win Allocate. So this is kind of this API takes care of a few things for you. And so in this case, if you don't already have a buffer, but you want to create one and make it remotely accessible, MPI Win Allocate is a good choice. It will allocate your buffer for you and directly make it remotely accessible once this function call returns. MPI Win Create, you might want to use this if you already have allocated your memory, but it's not yet remotely accessible. In this case, MPI Win Create, you supply your pre-allocated buffer, and MPI will make it remotely accessible. MPI Win Create Dynamic is a little bit more flexible. So this is, you don't yet have a buffer, but you will have one in the future that you want to make remotely accessible. So you can kind of just create a window object that then you can dynamically add and remove buffers to over the course of your application. And we have some examples of that as well. And then the last one here, MPI Win Allocate Shared. This is kind of a special purpose thing where you can create a window for processes that are on the same node can share, are able to share a buffer. And so this can take advantage of some shared memory communication optimizations. But this is, because it creates a window object here, we list it with the other MPI Win window creation functions. And just a note about performance versus flexibility. So we listed them in this order. This is kind of the least, MPI Win Allocate is kind of the least flexible of these APIs. And in most cases, it's going to give you the best performance. And then as you kind of go down here, the MPI Win Create's a little more flexible, right? You can give it the memory you want to expose. MPI Win Create Dynamic, you don't even have to have memory yet. You're going to add it later. These are more flexible interfaces, and they may lose performance because of that additional flexibility. So just something to be aware of if you're using them. Yes, go ahead.
Yeah, I never used this, and I was wondering, do all the processes need to create the buffer of the same size?
No, and so as we get into the syntax later, no, there's no requirement that you have to symmetrically allocate memory on all of the processes in a window. Some processes can contribute, memory. Some processes can contribute no memory at all. That's perfectly legal. Yep. All right. How are we doing here? All right, so we'll start by looking at the MPI Win Allocate API. So again, this is kind of the least flexible of the window creation APIs. And we'll just go quickly kind of argument by argument here on what you're doing with this API. So we're going to create a remotely accessible memory region in an RMA window. And the important thing to note here is that only the data exposed in this window can be accessed with RMA ops. So if you're now there is some for processes that can access that, right? The processes that own the remotely accessible memory, they can actually modify the memory locally without RMA operations.
Without the synchronization.
Without the synchronization, and that's that goes to the memory model stuff later on. But in any case, you know, for the purposes of this tutorial, we're going to focus on accessing this memory through RMA operations, MPI put, get, accumulate that we'll talk about later. So just quickly through arguments here. In this case, we're going to allocate memory. So we have a size. And this is, again, these are per process values. So in my local process, I'm going to allocate this many bytes of local data and expose it through this window. The displacement unit, so we'll see later in the communication APIs, the way you address this memory will be in numbers of this displacement unit. So this displacement unit is just some byte value that you supply in. An info argument, so info and MPI, how many people are familiar with the info system in MPI? I got a few, not too many. So info is kind of this built-in extension mechanism into many MPI APIs. And so what it is it's a very generic thing. You create what's called an info object, and you set values in that info object using these info set, info get APIs. And what those are hints or say promises to the MPI implementation about the behavior of your application. And so you can tell MPI certain things about the way you're going to create this memory or the way you're going to use this memory in order for it to possibly optimize it better than it would if you didn't supply this information. So info is just it's a extension and kind of hint mechanism to the MPI about how you're going to be accessing memory in this window. And I don't know if we have examples in the slides of actual info values themselves, but if you look in the documentation, you can see what is available and think about how you might use that in your application. As I mentioned before, window creation is a collective operation, and so you're going to supply a communicator as argument to this window creation function that tells MPI all of the processes that are going to be participating in the window. It also gives it a way to communicate in order to allocate or create the window itself. Base pointer. So we had the size here in the first argument. The base pointer is the actual pointer to the exposed data. I believe this will be an output argument. So MPI is allocating, in this case, we're allocating the buffer for you, and it's going to return to you the base pointer of the exposed local data in your process. And then you get back a handle, which you can supply to MPI later on when doing operations on the window itself. So just a quick example, pseudocode example of when allocate, actually maybe, yeah, pretty much pseudo. No, this probably would actually run and compile if he ran it. So this is a simple example. We initialize and finalize MPI, and then the first thing we do here is allocate a window where this is a symmetric example. So every process within MPI COM world is allocating an array of 1,000 integers. It's going to be using the size of an integer as its displacement unit. It's supplying info null here, so I'm not giving any hints to MPI in this case. This is a special value made available in the MPI.h header file that if you don't have any info to supply to MPI, you can just pass this MPI info null special value. Our input communicator is MPI COM world. Our locally accessible memory, right? That the memory that MPI is allocating for us, we're going to store in this pointer A, and then we're going to store the handle to our window in this variable win. So now array A is accessible to all processes in MPI COM world, and we'll get to the communication examples later on. And just to highlight here at the bottom, when you're done with a window, in order for MPI to properly free all the resources associated with that window creation, there's this call MPI win free, which it'll handle in this case deallocating the memory it allocated and freeing the window itself, freeing the window object itself. Any questions on when allocate? Question?
So let's say there are two processes, 1 and 2, and one has to put data into. So the memory in one, does it have to be part of a window?
It doesn't have to, no. The memory that you're communicating out of on the origin side. So I should explain also that my use of the term origin and target. So in MPI two-sided, we often describe things as a sender and a receiver. In one-sided communication, there's the origin process, which is going to be issuing the communication, and the target process is where that data is going to be read or written, where that memory is located, which is going to be read or written from, written to. And so in this case, right, the window operation, the put, the get, is happening at the target within that remotely accessible memory. But on the origin side, it does not have to be in remotely accessible memory. It can be private memory. Yeah.
Might have missed. How do you control how much of those memory gets allocated on each of them?
Right. So maybe Siri can answer. So in this case, it's a very simple example. We're allocating the same amount in each process. If you wanted to have different amounts on different processes, you would, it's like the domain decomposition step in the example code. Based on maybe the rank of your process in the communicator, you may decide to allocate some, a different amount of memory. And so I think we have, I think in the RMA example itself, well, that is kind of part of the domain decomposition step, is the processes instead of, I guess not necessarily in the decomposition step, but the processes kind of decide which parts of their memory they're going to expose based on whether, say, they're an internal region, an internal process in the mesh, or on the borders.
In this case, how is it possible to use A to access the same kind of size memory on all the nodes?
Is it process? Sorry.
Use A or Win to access, let's say, the Win1000 int on another machine.
So no. So A here is local. A is what you've allocated locally. That's it's your private memory. It is remotely accessible, but it's only remotely accessible through this window handle. So what I mean by that is. If someone else is going to write to A, right? Say I'm process 0, I allocated 1,000 integers. They're not going to target A. They're going to target the window that was created where your memory was made remotely accessible, and they're going to target your rank in that, the window, your rank, and some displacement unit in that window where they're going to read and write memory. But the A itself, this is local memory.
Thanks.
Say you didn't allocate enough shared memory on a node, and you pass in, I suppose, too large of data for the win handle. Does the API have an error handler for that, or is it just a lead?
So let me make sure I understand the question. So you say you're attempting in this case to allocate more than maybe the system can support.
So I think the question was if you've allocated less and you're putting more. If I understand it right?
Yeah.
Oh, I see.
Your put is bigger than the memory allocated.
Oh, then I mean.
Or part of the window.
Yeah. So, I mean, to give a little context about error handling in MPI is it's more or less an optional feature of MPI, and so the default error handling mode is essentially if an error is detected, MPI will crash. I don't know if. Yeah, in this case, I'm not sure we would even detect it because additional error checks like that in the communication path often add overhead and can reduce performance. So I think by default, you may not even see an error. It'll just be some silent, undefined behavior. But that's implementation dependent. Some others might check and return you some error. Yeah. Question?
Yeah, so when you want to put something in the remote memory of another process, so if I understand okay, you don't consider that a global address space is, you have to consider that you have decomposed it and then you have to...
Right, so when you're communicating with the remote memory, you're giving some target rank. So it's not like, yeah, you just have some one big array that you're offsetting into, that you're addressing target rank specifically. We'll see that in the communication code. So an MPI put takes a target rank as an input argument. So you're right. It's the window itself is conceptually global, but the way you interact with it is on a per process basis. Okay, so we don't have to spend too much more time on the other window creation examples, but we'll just highlight some of the differences here. So in WinCreate, so now rather than like in WinAllocate where the local memory array is an output argument, in this case in WinCreate we're supplying the base address of the local data that I'm going to be exposing in this case. So otherwise the call is very similar, but instead of the local memory being an output argument here, it's an input. And the example here kind of shows a little bit more how that might work. In this case, again, we're doing this symmetrically. This is a very simple example. We're using MPI alloc mem here, which is not required for your program to use the MPI alloc mem function, but it's just for example purposes here. There may be some benefit to it. It's kind of implementation dependent. So in this case, we allocate again the same 1,000 integer array. Again, this is private memory. We can use it however we like. We can initialize the values in it, and then we collectively in this MPI WinCreate call expose this memory. So A here is an input argument. We tell MPI the size of that local memory, the displacement unit, and we get back our window handle. One additional step here that's not in the allocate example is after we free the window, our memory is still allocated locally. So we have to, if you're using malloc, you would call free here. In the case here where we're using MPI alloc mem, we do MPI free mem in order to clean up the resources that we've allocated previously to expose in this window. So MPI won't free the memory for you if you're using WinCreate. Okay, create dynamic. So again, we're getting more and more flexible here in our window creation functions. So MPI WinCreate dynamic is actually fairly straightforward. It's just taking in a communicator and getting back a window object. You're not supplying any buffer, any size, displacement unit. In this case, you're just creating kind of like an empty window. Later on, I think I'll show the APIs for Win attach and detach. This is how you'll actually give MPI memory to make accessible remotely. And just, yeah, to be clear, the application is only going to be able to access that memory once the region has been attached. It can't access anything before that. And then, yeah, the window origin here, so because we have no base address or anything to start with, the window origin is going to be this special value MPI bottom. Displacements in this case are going to be addresses relative to MPI bottom. And I guess, yeah, so in this case, this is, if you're, maybe we'll see this in the example, but otherwise you must tell the other processes what your displacements are going to be after calling attach. I'm missing something conceptually there. Hopefully we'll cover it here in the example. So All right, here's our win create dynamic example. So again, we're just doing the bare minimum here. We're supplying null info, MPI com world, and getting back our window handle. Now we're going to create our private memory. After the window's been created, we're going to go ahead and allocate our private memory. Here we're using malloc as opposed to MPI alloc mem in the previous example. Again, once our memory is allocated, maybe we'll go ahead and initialize some values. And then here, this is a local call. We're going to call MPI win attach and declare this memory as remotely accessible. Now this is after win attach has returned, array A is accessible from all processes. So this is, again, this is all very straightforward, kind of straight port of this code previously. Accomplishes the same thing. It just shows how the flexibility of it in this case. But yeah, so in win attach we don't give a displacement unit. So that's up to. I suppose this is actually up to the MPI processes to agree on through some other channel in this case, as opposed to when you're using the displacement units in the creation call itself. So again, more flexibility, but that may impact performance because MPI doesn't know the displacement unit ahead of time, so it can't do any optimization on it. When your buffer is done, when you're done with your buffer being remotely accessible, you go ahead and use win detach to tell MPI, all right, this buffer no longer needs to be accessible remotely. Go ahead and detach it. And then yes, you still have to free it yourself here. The code is structured a little oddly here with multiple statements per line. But we go ahead and free the buffer that we allocated locally, and then we can free the window. In fact, we could probably do this we could probably free the window and then free the array as well. That ordering is a little odd compared to the previous example. Okay, so that covers window creation. We also didn't cover shared memory, win allocate shared, but that might be in the right. It'll be in a later section. So for now, we'll just focus on the regular remotely accessible windows, and we'll talk about data movement to and from that remotely accessible memory. So these are the data movement APIs in MPI. We have MPI put and MPI get. We'll talk about those first. Those are kind of the simplest. And then we have MPI accumulate, get accumulate, compare and swap, fetch and op. These are atomic operations, and we'll talk about what that means and why you might be interested in that when we come to those slides. Okay, so put is pretty much, this is pretty much what you might think of when you're thinking about remotely accessible memory. This is very similar to a send receive like operation. It's just that it's all happening on a single process. There's no receiver in this case. There's only there's only kind of conceptually a sender. And so and therefore the API itself ends up looking a lot like an MPI send and an MPI receive call kind of combined into one. So in this case, again, I talked about the origin and target terminology. We're moving data from an origin in local memory to a target process, which is remotely accessible. We have separate data description triples for both the origin and the target here. So you'll see that we have an origin address, count, and data type, and also a target displacement count and data type. So again, we talked about how the basic types, the type signature in MPI has to match in order for a send and receive operation to work correctly. Here, it's the same principle. So I can have memory that's in non-contiguous data on my local process, and I put it to contiguous data. Similarly, or conversely, I have contiguous data I want to put to non-contiguous region on the target process. That's all allowed. MPI will handle the transmission of the shape of your data in a one-sided communication. So again, the receiver is not involved. They don't have to know any of this information. Okay. Get is similar to put, except rather than writing data to the target memory region, we're going to be reading from it. So again, an MPI get, you're moving data to the origin buffer from the target. And similarly, the API looks very similar here. We have our origin adder, which address which is in our local memory, account and a data type. We have our target rank in the window, and we're going to be reading from the target displacement for this many count of this data type that's been exposed in the RMA window. Questions about the put and get APIs? Yeah.
Yeah, in MPI send and receive, I understand that each one can have different counts, and it makes sense. What does it mean here? Do you have to be different origin count and target count?
Right. So, for instance, if we're say maybe we're using some derived data type on the target side, or you know, let me try and think of a good example. But one thing that is possible, this is probably you wouldn't do in a real application, but okay, so I have some contiguous buffer here on my origin, in my origin memory. So I have a contiguous buffer. Maybe I created an MPI type contig. Therefore, I have 10 integers, but my origin count is only 1 because it's a contig type. But I put it into some, those are the types of things. So we have to specify both because while the type signature has to match, the shape or the layout of that data might be different. And therefore, it's a really general interface. And under the covers, MPI has to do a lot of work in order to transmit, the target data type in cases where it is some complex type. But we do that in order to give users some more, more flexibility. There's some specialized APIs later on that kind of restrict what's possible within the communication, and therefore it hopefully will perform better on certain architectures. Question?
So how would you control on the target side the order of when you put in stuff before the origin can grab?
We'll come to ordering in later slides. Yeah. That's a good question, and it's a little complex. We'll try and cover that. Okay, so those are basic data movement APIs. Now we'll talk a little bit about the atomic APIs in MPI RMA. And so the first one here we'll talk about is MPI accumulate. So accumulate is an atomic update operation similar to a put. So the argument list here looks a lot quite similar to MPI put, and in fact we're doing a similar type of movement where we're moving some data from the origin to the target remotely accessible memory. And in this case, it's going to be reducing the origin and target data into the target buffer using some operation argument as the combination, as the reduction operation. The ops here are restricted to the predefined operations that are defined in MPI. You'll find these in the MPI documentation. They're usable as well in the reduction collectives that we covered in the previous section. But the caveat here is that while in collectives you can define your own reduction operations, those are not allowed in MPI accumulate operations. Like MPI put, different data layouts between targeted origin are okay. That's still allowed. But the basic type elements must match. And I guess this is even more restricted than the type signature must match. Because we're doing operations here, we're doing, say, a sum or a product, the types themselves, you can only sum an integer with an integer or a floating point with a floating point. That's a requirement of this API. One special note here about the operation, the predefined operation MPI replace. If you use that in combination with MPI accumulate, it's kind of like an atomic put. And when we talk about ordering later, we'll see why that why that might be important for your application. Get accumulate, again, this is kind of builds upon what we talked about when talking about MPI get. So MPI get accumulate is an atomic read, modify, write operation. Again, it uses these MPI predefined operations as a way to operate on the data in the target memory. So in this case, we have our argument list here has actually grown a little bit. So what's in red is the result address. This is also local memory, where you're going to be. Is this local memory? The result address is in local.
Yeah, it's like a
Okay.
It's like a get, yeah.
Right. Okay, so how do I origin data stored in result buffer, different data layouts. I think that's actually.
That's where the result of the get of the accumulate.
The result of the
It
accumulate.
gets the previous and accumulates the.
Right. Right.
And the fetch and increment.
Right. So you're getting. Sorry, these APIs get a little complex. So you kind of have to consult the documentation each time you're kind of modifying your code. But I think the idea here is right. You have some origin data that you're going to transmit to the target side, perform an operation on in combination with the target memory address, and then the result of that operation is going to be stored in the result address buffer here. So again, your target and origin data layouts can differ, but the basic types have to match. And if you're using an MPI no-op operation, this can essentially be an atomic get. And similarly, if you're using, you can implement an atomic swap operation if you're using the MPI replace predefined operation in MPI. And then these are kind of simplified or slightly restricted versions of the accumulate operations. So the fetch and op, MPI fetch and op is a simpler version of MPI get accumulate. Its buffers all share a single predefined data type. The count here, we're only using predefined data types in this case. Derived data types are not allowed. There is no count argument. It's always going to be 1 in this case, so you're operating on a single element in memory. And the idea is that these simpler interfaces allow better hardware optimization. They kind of more closely align with what hardware is able to do. Compare and swap here is another simplified operation where it does an atomic swap if the target value is equal to the compare value being supplied as part of the API here. So that covers data movement. Any more questions? I know those are really complex APIs. Like I said, you might have to consult the documentation, each time you go to use them, just to make sure you have things straight. But any other questions about those at this point? We'll move on to ordering. All right. So ordering of operations in MPI RMA. So this is the important stuff. What you need to know if you're going to be using these APIs. So there's no guaranteed ordering of put and get operations, like the question was asking. This is true even of put and get operations done from the same origin to the same target process. There's no guarantee of ordering. If you're doing concurrent puts to the same location, whether it's from the same process or different processes trying to remotely update a memory location, the result is undefined. You might get one value, you might get the other value, you might just get garbage. The MPI implementation is kind of unable to guarantee anything for you in that scenario. So you have to program your application accordingly to make sure the result of some location update makes sense to you. Result of concurrent get operation with a put or accumulate is also undefined. So if you're doing a write and a read concurrently within the same epoch, we'll talk about epochs I think in the later slides. There's no guarantee that memory location is going to be consistent when you go to read from it, so it might be garbage. Result of concurrent accumulate operations to the same location in memory is, however, defined according to the order in which they occurred. And so atomic put, so like I mentioned on the slides where we were talking about accumulate, you can actually implement an atomic put operation if you do accumulate with MPI replace, or an atomic get with MPI no op, get accumulate with MPI no op. So we have some examples on the slides here to show how you might use these to ensure some sort of order in your application when using RMA. Accumulate operations, unlike put and get, accumulate operations from a given process are ordered by default. So if you're using accumulate from an origin process more than once to the same location, then MPI is going to guarantee those operations are ordered. You can, however, tell MPI that you don't require that ordering. So maybe you're not going to be doing you're not going to be doing concurrent accumulate operations to the same location from the same origin process. If you're not, it might be a good idea to tell MPI you're not going to be doing that. Therefore, it can do some, relax some restrictions internally in order to optimize communication. You would do this through that info object I talked about during the window creation slides. There's some things in the MPI standard that'll where you can tell MPI your ordering requirements. You can also ask for specific orderings that you need in order for your application to work. So there's some predefined ordering values. You can tell MPI, I only need read after write ordering, or write after read, write after write, or read after read, write after write. So this is all kind of nitty-gritty details, but consult the documentation of MPI or ask questions if you want to know more about those optimization hints. So here's some examples of ordering just to again kind of reinforce what we're talking about here. And these are simple two-process examples and trying to show you what is and isn't defined or guaranteed by the MPI library. So in this case, process 0 is doing concurrent puts to the remotely accessible memory exposed by process 1. So here it's writing some value 1 into remotely accessible memory at, say, location X in this case. And then so it's doing a put 1, put 2 into some memory location at process 1. Well, it's entirely legal for this second put operation to occur before the first one. And therefore, this the state of this memory is undefined. In fact, not only could it be one or either value, it could also be garbage. MPI could just kind of corrupt the memory in this case. Second example here, we're doing a concurrent put and get to the same memory region on the target process. So the idea here was I'm going to put the value 2 into process 1's memory, and then I'm going to get that same memory location and retrieve it locally here, and say it was previously initialized to some value 1. Well, in this case, yes, the get is allowed to complete before the put has updated that memory location. So you might get 1 despite the fact that you think you've written 2 to that location previously to issuing the get. And then the third example here on the bottom is an example where ordering is guaranteed by MPI. So the first thing we're doing here, process 1 is initialize this memory location X to the value 2. I'm doing a get accumulate operation where I'm retrieving the value 2 to my local memory. In this case, I'm adding 2 to the value, it looks like in this case. So I'm getting back the value 2 that was initially stored in that memory location. And then the accumulate operation I do after my get accumulate, where I increment the value again, is guaranteed to happen after the get accumulate that I issued previously. So let's clear up some of the ordering questions we talked about. So we've covered window creation and data movement. Now we have to talk a little bit about synchronization. So great, we're reading and writing remotely accessible memory. How do I know, when to act? This is kind of the complex part of RMA, is that, again, the target is not involved in the data movement. Therefore, it doesn't necessarily know when its memory has been read or written. Therefore, we have synchronization models defined in MPI that there's a couple different models that you can choose based on your application. And so the idea here is, right, I was kind of introducing this, that when do I know when my memory is ready to read? When do I know when I've the operations that I've issued have completed at the target? So there's three synchronization models we'll talk about. First is fence, and in parentheses here we call this active target. So I guess we'll get to this in examples, but this is more where everybody is kind of, it's almost like everyone in a window is participating in all the communication. There's kind of like it's almost like a barrier semantic when you call this MPI fence operation. The second synchronization model is post-start complete wait. This is a more generalized version of active target. It's not really used, so I think we're going to skip over it in the interest of time. And then the third synchronization model is what we call passive target, where the synchronization is actually done entirely on the origin side. There's no, the target doesn't even participate in the synchronization. It's only the origin side that we'll call these lock-unlock functions in order to synchronize operations. I touched on this a little bit earlier. Data accesses occur within what we call epochs or epochs in MPI. There's a couple of different things we mean when we refer to epochs. So there's an access epoch, which contains a set of operations issued by an origin process. There's exposure epochs which enable remote processes to update a target's windows. The exposure epoch is something on the target side, some frame of time when remote processes can update the window. Ordering and completion semantics are defined within epochs, so that's the purpose that these things serve. And our synchronization methods are the method of establishing epochs for your processes, starting, ending, and synchronizing. So let's look at the first example of fence synchronization, active target synchronization. So this is an MPI WinFence API. It's fairly straightforward. It only has 2 arguments here. It's a collective synchronization model. So like I said, it's kind of like a barrier. It's not exactly like a barrier, but for conceptually you can kind of think of it that way. MPI WinFence will start and end an access and exposure epoch on all processes within the window, right? So there's 2 different types of epochs. There's access and exposure epochs, and fence starts and ends both of those types of epochs. Like I said, this is collective operation, so all processes that are in the group of the window do an MPI WinFence to open the epoch here. So on the diagram on the right here, we do an initial fence here to start to open the epoch. Within the fence, after the fence, we issue our put and get operations to read and write data. And then at the end of the epoch, to close the epoch, we call WinFence again. Then the memory, the RMA memory is then defined at the end of the fence operation. So that's the idea of active target here. I forget what the assert argument here. What's that for?
That is to say, whether it's starting an epoch or not, is it with the other fence semantics? Is this?
I see.
I'd say we can ignore.
Conceptually, it probably doesn't matter. You can look at the documentation. Yeah, there might be some optimizations you can do with this assert argument, but really it's it's very similar to a barrier here, where you give it this collective window object, and it starts and stops the exposure and access epochs. So this is the simplest synchronization method, and it's actually the one we're going to use for the next example. All right, so what we're going to do, we're going to build upon the same stencil example you did in the previous session. We're going to re-implement the data movement as opposed to using send-receive, using RMA fence synchronization. And so we can go through this after I cover the rest of the slides. But we have a couple of different solutions available. The first one you can tackle is using MPI put to do this halo region exchange as opposed to send and receive, and using fence, MPI win fence to synchronize when the data movement is complete. So we'll come back to that. We can also, we have further example solutions that use fence with get as opposed to put, and a few other, and I think there's one other example at the end of the section. So contrasting with the active target synchronization, the barrier-like synchronization of MPI win fence are passive target synchronization in MPI. So this case, we talk about the lock and unlock models in MPI RMA. So the lock and unlock here, we didn't cover post-start complete wait. So just think about this. Think about these dotted lines as like fence operations we covered before. But in passive target, even the synchronization method we're using is only happening on the origin side. So we're calling this lock function, we're issuing some data movement and calling an unlock function. And again, the target side is not involved at all in synchronizing with the origin on data movement. This is more like a shared memory model. If you're familiar with using, say, shared memory within a node, you might acquire some lock, update some value in shared memory, release that lock, and somehow the other processes that want to read that value will have to know when that might be safe. So these are the APIs involved with passive target synchronization. So like I said, we have lock and unlock functions. And then in order to complete operations, we have these MPI win flush and MPI win flush local APIs. So lock and unlock, this is your method for beginning and ending a passive mode epoch. Target processes do not make these corresponding calls. This is all on the origin side. You can initiate multiple passive target epochs to different processes. You can kind of nest these things. That's not, you can't nest epochs to the same process, but you can have multiple open epochs to different processes all happening concurrently within the same MPI process. Yes, like I said, you can't have concurrent epochs to the same process. There's two different lock types. There's shared locks and exclusive locks. Shared locks mean that other processes can access that target process's remote memory concurrently. You just have to be careful about how you access the memory if you're going to be potentially accessing the same locations in the RMA window. Exclusive lock is a little more restrictive, where you could say essentially, I'm locking this target process's window exclusively for my access, and therefore MPI will guarantee that no other processes will access it concurrently in that case. The flush APIs, the flush here, as opposed to flush local, flush is what you would use to remotely complete RMA operations to the target process. So I've done some put, get, accumulate operations to the target process after I've locked the window. If I call win flush and it completes, that means the data can be read by the target process or any other process that then acquires a lock to read and write the data from that target process's window. Flush local is a guarantees slightly less here. This only guarantees the local completion of RMA operations to the target process, meaning that read, put, get, accumulate operations that you've issued from your local process, that those are then complete locally, but it makes no guarantee about what's happened at the target window. So the state of the memory on the target then is not guaranteed by the flush local operation. And a slightly more advanced version of passive target synchronization also exists. This is the MPI win lock all, unlock all APIs. And similarly, we have flush all and flush local all operation completion APIs. So lock all is a shared lock, always a shared lock, passive target epoch to all other processes in an MPI window. So you can essentially say, I want to access all other processes in this MPI window's remotely accessible memory. Therefore, I issue this lock all API. The expected usage of this, because this is kind of this can in practice be kind of expensive, is that if you're going to be doing a lock all, it's kind of a long-lived exposure, or it's kind of a long-lived epoch. You're gonna do a lock all, do a bunch of put and get operations, flush them, maybe repeat, do more put and get operations, flush those, and then eventually when you're essentially done with the window, you'll unlock all. That's kind of the intended use case here. You wouldn't be doing lock all, unlock all multiple repeated times throughout the course of your application. And then yeah, the flush all and flush local all APIs, much like on the previous slide, these guarantee the remote completion of RMA operations, in this case to all other processes in the window, as opposed to just a single target, and local all as well. It locally completes all of your operations issued to all other processes in the window. Yeah? Is the target forbidden from accessing its memory when it's locked?
Is that?
Yeah. What's the...
The window memory, it should access that using the lock, unlock functions out there.
So I think it's encouraged. I think the answer is, or sorry, the question is the target process forbidden from accessing the memory that it's exposed while it's been locked by some other process? And I think the general practice is if you want to access your remotely accessible memory, even locally, you should acquire a lock to it to guarantee the state of that memory. Question?
How's the support for this paradigm for accelerators? So you have CUDA-aware MPI where you get this RDMA for CUDA buffers, you don't need to copy the host and transfer. So I was wondering, with this, can you access memories in accelerators? Is this something?
So you can use this. You can use this to access memory on Accelerator. The performance will be heavily implementation dependent. So it may not be possible for an implementation to use hardware to read and write from GPU memory. I don't know if there's any technical limitation to that, or it's just the implementations haven't yet gotten to that point. I know that, for instance, with point-to-point operations in CUDA-aware MPI, you can achieve really good, performance using the hardware. Will use RDMA underneath the covers to directly read and write to GPU memory. As far as one-sided, I don't know if the implementations have gotten all the way there yet. But I don't see any reason why they can't in the future. For instance, in MPitch, our support for NVIDIA GPUs and AMD GPUs, the RMA operations won't actually be issued in hardware. There will be some software emulation happening underneath the covers. But you still can, like I said, you can use GPU buffers in this case. It's just your performance. The performance you get might look a little strange because it's doing a lot of software emulation in order to work correctly. Yeah. Question.
So, under what circumstances is it beneficial to be flushing RMA operations?
Oops, sorry, clicked way ahead here. So, yeah, that's a pretty good question. So what's the, I think that Rajeev's my RMA expert, so I keep
So it's not
turning to
beneficial,
him.
it's more for semantics, it's for your program.
Yeah, I think it's kind of program dependent. So in this case, you would kind of maybe you're doing some bulk synchronous operation, or you're iterating through some time steps, and so you're doing some set of data movement, and then before moving on to the next time step, for instance, you want to make sure that all the operations are complete, so you can then do your floating point updates and things like that. So I think that flushing is more of kind of like a lightweight synchronization as opposed to a heavyweight fence or a barrier or a reduction. You kind of do a lightweight, okay, my data movement is done, I'll shift over to compute and then maybe issue the next set of data movement operations. So think of flush maybe as, especially with this lock-all type of passive target synchronization, you can see here that our heavyweight synchronization is only happening at the start and end of the RMA exposure, and then within we do data movement and kind of flush is like a lightweight synchronization. Okay. And so I think just a few slides left here. So one of the common questions we get about RMA is, why should I use this? What's the use case for RMA as opposed to MPI two-sided? And so as a use case, we use an example here of an application, a big DOE application, NWChem. This is a high-performance computational chemistry application suite. I couldn't tell you all that it does, but the main takeaways here are that NWChem is a very large code base. It's about 4 million lines of code, and it has quite a bit of capital investment by DOE and other research institutions. To date, they estimate maybe $200 million have invested in the development and maintenance of the NWChem application. And the NWChem applications uses an abstraction called global arrays. Global arrays is this library it's essentially a programming model that is based on the idea of a global address space, as opposed to MPI, which you're thinking a lot about kind of local memory. The global arrays has this global address space. And then beneath the global arrays implementation is MPI RMA, actually handling the communication and data movement to facilitate this programming model. And the reason MPI RMA or RMA-like APIs fit this well is that this is more of an irregular application than say a bulk synchronous nearest neighbor data exchange. You have this really large array, and it's going to be updated kind of randomly from other processes, and it's not a very predictable pattern. And so this is kind of a simplified view of how this might look. In practice, this is consider, say, a 2D array of floating points, and you're going to be multiplying these, and it uses this get compute update model of communication in order to update the array in the global address space. And so because, again, we've got non-contiguous data here, which MPI can handle well for us. And in this case, the communication is very irregular. So RMA is a little bit better where, especially passive target RMA, where you don't know who's going to be communicating with you and when. RMA is kind of a good semantic fit for this type of operation. And again, this is simplified. This is showing 2D matrix multiplication as opposed to the reality, which uses a far more complex data structure. So that's kind of one real world use case of RMA. And the important part is if your application is irregular, you don't know who your communication partners are, or you don't, or they change over time, RMA might be a better semantic fit for your algorithm as opposed to send and receive, where you kind of have to have this pre-existing knowledge of who your communication partners are. And then just this is kind of following on that same thought process. Which synchronization model should I use and when? RMA, in general, just as just kind of a general statement, will have low overheads versus send-receive. Because the two-sided interfaces, there's this matching, queuing, buffering, other things that are required of the MPI implementation that's not required for one-sided. One-sided is kind of designed to be, close match to RDMA functionality that's available in hardware like in InfiniBand. Though the caveat here is that good two-sided MPI implementations also use RDMA. So that's not strictly true that RMA is always going to be better because it uses RDMA. It's two-sided can use that as well, but it has this additional overhead of message matching. But when would you use one synchronization mode versus the other? Active mode, if you're doing bulk synchronization, like I talked about, the ghost cell exchange, like in the example, active mode is probably good here because everybody's kind of communicating at the same time, the same amount of data. Passive mode is maybe preferable if you're doing asynchronous data movement. So if you've got really large data sets that maybe you have some global array because your data structure spans the memory of multiple nodes. If your data access and synchronization pattern is dynamic, like I talked about, you don't know who or when you're going to be communicating with others. And so that, yes, this distributed or shared array example is kind of a good example of when passive mode synchronization is a good idea. And then within the passive target lock, within the passive modes, when do you use lock unlock versus lock all and unlock all? So lock unlock is useful if you are going to be using exclusive epochs. Lock all, unlock all is if you're only using shared epochs, there's no point in using lock and unlock. Just use the all versions of those functions, and therefore you can kind of have shared epochs with everyone else within the window going all the time. And so yeah, that takes us to, I think that's the end of the one-sided slides. We'll go back to the example, but in the meantime, if you have more questions, please let me know. All right, so the example, like I said, so hopefully you've gotten through the derived data type example we introduced in the last section. If not, you can kind of start from the solution that's in the derived data type folder. But the idea here is, previously we were using non-blocking send and receive communication to do the data movement. We used derived data types. Now, instead of using MPI send receive, let's use MPI put and MPI fence to perform the communication and replace the send and receive calls. There is a solution available again in the RMA directory, so take a look at that if you're stuck. But otherwise, ask us questions and we'll try and help you along with that. We go up to 12:30 before lunch.
Yeah, they've given us that time slot of 12:30 for lunch there. Yeah, there's a question.
Should we do the collective one first or the RMA one?
Oh, good point.
Oh. I'd say since RMA is fresh, why don't we do the RMA, you can ask questions. The collective one is the all-to-all is a little complex. We can leave that for the evening or later. There are actually three exercise examples in RMA. We can do the other two in the evening because we might start with Yanfei's part in the afternoon and see.
Okay, so welcome back. So the next set of topics is related to what we call hybrid programming with MPI, and specifically with thread shared memory and accelerators. Okay, so this is what we usually refer as MPI plus X programming, where the X here is, depending on what you use, could be thread shared memory or accelerator. If you compare this essentially is whether you have threads on the same machine or whether you create a shared memory region. In this context specifically, it's related to the MPI shared memory, which I will talk about later. And the last thing is accelerators. So MPI plus threads. The reason why we started to have this hybrid programming model with MPI is related to one is what the applications need is strong scaling. That's probably the most important part for the application. We want to improve the performance on strong scaling, but with the evolvement in the HPC system, this is becoming harder and harder if you're trying to run a larger problem or more complex problem by simply just increase the number of cores and have one MPI process running on each core. The problem is that some of the resource in HPC is not scaling linearly as it is with the CPU cores or the flops, right? For example, your communication bandwidth per node is limited, and the memory is limited as if you for one node that has more cores than before. Okay, so all those cores have to share the same the memory space and the communication bandwidth. So just doing pure MPI on these processes is making things harder to get a better performance. Okay, so that's why some of the application and the application developers I have started to explore the uses of threads in combined with MPI. So some of the benefit might be you can the library itself could use less memory, because now instead of having each core has its own MPI library and allocate the internal data structures for whatever the library is using. Now you can have all the cores sharing one copy of MPI internal resources, but still exploit the parallelism of multiple cores through threads. Okay, so that reduced the memory consumption, and also another thing is essentially for using one MPI process per node instead of per core, you're also like reducing the amount of communication that is happening in terms of the scale of communication. Because if thinking about if you're doing a collective call, and if you have, instead of having one process per core, if you have one process per node, essentially you're reducing the number of processes that is participating in one collective calls. So essentially, it reduces the overhead. It reduce the overhead and makes the communication a lot simpler. Okay, so one example for that is NEC 5000. It's trying to exploit that, and also another great example for MPI plus thread is QMC pack. This is more related to what I just mentioned by reducing the memory consumption. But in this scenario, it's not the memory consumption of the library itself, it's the memory consumption of the application. So in QMC pack, there's each process has to maintain a very large B-spline table for the data. And what happens if the content can be essentially is duplicated if you have multiple processes per node. So what happens is they trying to using threads to allow the work unit on the nodes to share the same table. So essentially reduce the duplicated data and increase the size, increase the problem size that can be run on the given memory side. So how to do MPI plus thread? A simplest way, if you look at this very small example here, we have 4 nodes, and each compute node has 4 processors. And if we try to run the 5-point stencil example as we did in the hands-on, with pure process, we would end up some some kind of the data decomposition like this. So each of the core are, each of the process on this core are responsible for a 2x2 grid. But if you look at the halo region that we have to allocate it for them, it's even larger than the data that you actually doing calculations on. Although this is a very extreme cases, but the surface to volume ratio in this scenario is not very good. But if we switch to MPI plus threads, essentially we kind of removed all these halo region in between these. Okay, so you only have this outer boundary as your halo region, and all the data, these 4x4 data on the same node are processed by, in this case, 4 threads. Okay, but you reduce how much communication is needed between the nodes, and also if so it kind of reduce the memory consumption and allow you to have a smaller buffer size for these problem. And also with resource, you can do something like fine-grained communication. If you look at the process version, essentially, like we just did, essentially we have some computation and everybody just stop doing computation and send receive a bunch of message and then do the next iteration. But with thread, so there's a lot of exchange happening in between each iterations, which what we usually refer as a box synchronization model. But ideally, if you have threads and each thread can, let's say, doing the communication that it has. Okay, so instead of having the process to wait and communicate the entire boundary to the neighbors, each thread maybe can take it small pieces and exchange with the corresponding neighbors for that small part of data. So ideally, we can have a lot of small communication, which can be a lot faster, and potentially have an asynchronous tasking model to have it work. Okay. So as I mentioned, so with MPI plus thread, how we can do this? Okay. So the general guideline is MPI is essentially good for the communication or the parallelism in between processes, or in this case, let's say in between isolated memory spaces. Okay, so on the same node, you can use thread, and they will share the same memory address space, and then between nodes, there will be taken care of MPI. So it's kind of two-level parallelism. And for the threading part, the most common building blocks would be OpenMP, or if you would, you can write pthread, but I think most of the scientific application prefers using OpenMP for the simplicity and the programmability. Okay, the only thing you need to be careful with MPI plus thread is now depending on how you do the multi-threaded communication or not doing multi-threaded communication, the MPI library has to provide certain thread safety for the interoperability between the MPI and your threading library. Okay, so in MPI, we have 4 different levels here. So we have the MPI thread single, which is essentially no thread support, to the most flexible way that you can do MPI thread, that every thread can do MPI communication. The takeaway from here is, as you're choosing a model that is more flexible for you to do multi-threaded communication, there's more overhead or more thread safety needs that the MPI library has to provide. So the downside is there will be more overhead, and performance might not be very great. Okay, so to start with, the first thing you need to choose is what kind of threading level that you actually need to do. I have more examples after this, but the important thing is instead of using MPI init to start your application, you need to use MPI init thread. Okay, comparing to init, it has two extra arguments. One is requested and one is provided. So basically, this is saying, for example, I want to do thread multiple. I will use the init thread function to query the library, say, I'm trying to initialize an MPI environment with thread multiple. And the function can return, say, yeah, it's initialized. This is what you got. Or it can say, I don't support MPI thread, but this is maybe I only support up to thread funnel. And then you can come back and see, oh, if there's only thread funnel, how my application should change or have a different code path for that. Okay. So like I said, the basic one is MPI thread single. This is essentially saying I'm not using multi-thread support. The library is, you can consider the library as thread unsafe in this scenario. So essentially, this is equivalent to MPI init. And then the second level is MPI thread funnel. Okay, the difference between the funnel and the serialized is now I'm using thread, but I'm not doing any MPI communication within the thread. Okay, so the communication and computation are kind of interleaved. So imagine these are okay. So we have the example here. Basically, you have a function for doing the calculation, and you can create a bunch of threads and then wait for all the threads to finish before you issue any MPI communication. So there's two implications here. One is I'm saying I'm not doing multi-threaded communication. Okay, only one thread, and it is only the main thread that is doing the communication. So on top of that, there's MPI thread serialized, which is a slightly more flexible than the funneled. Essentially, we're in the thread serialized, we still say we don't do multi-threaded communication, but it is not the main thread that does the communication. So if you look at the example here, we moved the MPI stuff, which used to be here, into the thread function. But what we have here is we have a mutex locked to ensure that at any given time, there's only one thread can be doing an MPI communication or issuing a message. Okay, so this is saying that we essentially this is the responsibility for guarantee that only one thread is doing the communication is on the burden is on the developer. Okay, so and this is in terms of implementation, this usually from a library perspective is not so different from the MPI funnel. Okay, the last one is MPI thread multiple, which saying this, the user don't have to worry about the thread safety. The library is fully thread safe, and you can issue all the threads can be doing MPI call at any given time, and they can be doing this in parallel. So you don't need any critical region or wait for the thread to finish. None of those. So if the figures describe it, that is here. So as I mentioned when I was talking about MPI init thread, not all the thread support level is implemented in any given MPI library. It is so for most of the library it will have thread single, and also because the funnel and thread serialized is not so different. So those are mostly supported, and so only the thread MPI thread multiple level is considered to be fully thread safe, and it's not implemented by every MPI library, but for most of the library that you use on today's HPC system, this is supported. Okay, so the last thing very important. Always use MPI init thread to initialize an MPI plus thread program. If you don't do that, it'll probably work. If you what you want to use is like thread serialized or thread funneled, you probably won't run into problem, but it's still considered an incorrect program. Okay. So far, is there any questions about these 4 levels? No? Okay. Okay, so the next few slides that we are going to talk about is specifically focusing on the MPI thread multiple model. Okay, because this is probably what you really want, because for the most flexibility. Okay. So the one important there's 2 important things that you need to consider when writing a program with MPI thread multiple. First thing is ordering. So although all your thread can be issuing MPI calls, there's an important requirement that as a developer you have to make sure that the call actually can be completed in any order that it still makes sense. What happens is from the MPI perspective, it doesn't know that. Let's say you have two threads on one node, and there's two MPI processes trying to talk to each other. And what you might have in mind is I want thread 0 to talk to the thread 0 on a different process, and thread 1 goes to thread 1. But in reality is MPI library doesn't know that. From the library perspective, it knows there's someone or some threads has issued 2 MPI calls on my side, and there's other. So the matching order could be like in any way. So the ordering requirement in MPI plus thread with thread multiple is that you can have multiple threads issuing operations, but these operations has to be a valid application regardless how the threads are scheduled. Okay, we'll see some examples here after this. And the second thing is about progress. So this is fairly simple. So basically, if you issue a blocking call on on a thread, you only block that thread. Okay, the other thread can still come in and make MPI calls. The blocking call on one thread won't block all the process. Okay. So back to the ordering problem. So like I said, this is a very simple example. You have 2 processes. Each process has 2 threads. So one of the thread is issuing a bcast, supposedly with the thread 0 on process 1. And then thread 1 is doing a barrier with the thread 1. So this is probably the picture that's in the developer's mind, that thread 0 should work with thread 0 and thread 1 with thread 1. But this is not a correct program. And as I mentioned, because what can happen is when the threads are running or when the processes are running, there's no guarantee that which thread will run. Okay, so on process 1, maybe thread 1 gets scheduled first, and on process 1, thread 2 gets scheduled first. Then you ended up in a situation that you are trying to match MPI bcast with an MPI barrier, which both of them will block. Okay, so and then on the later end you have an MPI barrier and bcast trying to match with each other. So this won't work. Okay, so that's why I'm saying if you write a program, you have to guarantee that regardless how the threads are scheduled, or essentially what is the issuing order of these operations. it should still complete correctly, which is actually harder than you might thought. Okay, so this is one example. The other example is if I have one thread trying to do a communication where the other thread is trying to free that communicator. This is also incorrect because the thread could be free in the communicator before the BCAS is being called. Okay. The correct example in this scenario is if you use blocking call. Okay, this is a correct example because whoever got run first will block on the completion of the operation. So if the MPI send got issued first, then it will block the thread 2 there until the MPI receive on the remote process being posted. So eventually, if you think about that, in the worst case, there will be 3 threads in total getting blocked, and waiting for the last thread to actually run, and it will kick the communication back. Okay, so that's how a good a correct example will look like. Okay. So like I said, the current situation with the MPI is for most of the library, thread single and funneled and serialized are probably single will always be supported, and funneled and serialized are probably supported, although they may not say that. And thread multiple are supported by most major libraries. Okay, and when you write hybrid program, it's the developer's responsibility to make sure that your code is correct, regardless the execution order of the threads. Okay, so that's the takeaway. But the good thing is you can use the many popular commercial debuggers like if you have what I always use is an Anelia DDT, where it will show you how the threads are getting run if they are waiting. If their threads are blocking on different kind of resources, it will mark it up, and it will be easy to figure out there's some deadlock happening because maybe there's bad ordering of the code or issuing order of the operation. Okay, so far any question? Okay, then there's a question for you. Okay, so the following is a very simple MPI plus thread program. It's incorrect. It only has 2 processes, and each process has 2 threads. And what happens is sometimes when you run it, it will hang. Essentially, it will deadlock at some place. And it's actually, you will see it's actually using blocking communications. So how that happened? Okay, so this is the code. Okay, so this is one process, the red one, and let's say this is the green one. So essentially, if you look at the green one, it's doing 2 MPI receive from the other process. Okay, and then send 2 character to the opposite, and then repeat those 4 operations. So on the receiver side, there's 2 send matching these 2 receive, and 2 receive matching these 2 send, and then repeat. So this code, sometimes it will hang in one of these calls. Can anyone guess what's going on?
So the execution order is not guaranteed between the threads. So essentially, you could post a receive before you post a send.
That's close, but not quite what causing the problem. Okay, because this is blocking call, So as long as eventually someone is sending the message, it's okay. That at least that's what we have seen so far. Any other people trying? Okay.
Rank equals 0, not always satisfied.
This one, we only run with 2 processes. So there's always rank 0 and rank 1. Okay, so that's not the problem either. Okay, so as I said, this is what the developer has in mind that's supposed to happen. Okay, so basically it's one thread sending to the other thread, and then thread 2 send receive between thread 2 on the other side. Okay, but if you look back at the code, essentially you have all the operations have same tags, and the destination is the same. So what can happen is this. Okay, so let's say there's this could be a valid ordering when the operation is issued. Okay, so as you can see, if there's one receive on this thread intercepting one of the message that is being sent. Okay, so this thread is intercepting the message that's supposed to be received by this thread, and at some point they all call MPI receive, and the program just hangs. It's deadlocked there. So this is what basically this is how complex the things could be if you're doing MPI plus thread communication. But of course, in this extreme cases, because everyone is doing blocking call, if you can think about if everyone is issuing MPI I send and I receive and do a wait all after all the communication has been issued, it might not be a problem in this case, because at least not in this kind of scenario. Okay.
I want to see if they have understood the problem or what was done.
So,
are there any questions or what?
Any questions?
So how do you avoid this from?
Honestly, there's no easy way. I think in this particular scenario, I would just use non-blocking calls. It might be easier.
But there was a solution, that is to use a tag and the iteration number as a tag. So these are actually two loop iterations that you have unrolled and
yes.
shown it as one.
Oh yes,
and
yes.
The solution
right.
was to use the iteration number.
Yeah, that's
This code
true.
looks a little different to me because I usually present it with the iteration as a for loop.
Okay. Yeah.
So I'll just give you some background. Is this came to us as a bug report from a user that their code was not working, and they thought it was a bug in the implementation. And we simplified it to something like this. It was a little more. It had more iterations or something. There was more going on. And can you go back to the one slide? Where is the?
Yeah,
It really was a there was a for loop, I remember, which you have kind of.
Yeah, there used to be, but we kind of simplified.
Yeah. So I'm used to seeing it in that version. Yes. When you look at the code, it looks like it should work, but when I debugged it by going inside the implementation to see why it is hanging, because in a threaded case things can hang quite easily. It turns out it was a user error because they were assuming that the threads are running in some order, and that one thread doesn't race ahead into effectively the second iteration of the loop. So where here, if we, I'm finding this one a little hard to follow myself. This
yeah.
Yeah. Can you say where the hang occurs here?
The hang is actually here, where in In a
Right,
case
and
where
why has it reached that stage? Is because
because
some
the thread 2 is intercepting the message that's supposed to go to, or intend to go to thread 1, but only intercepting one of them, and it's basically this crossover here.
Yeah, which specific message are you like the 2 sends of thread 2?
The two sends are being received by 2 receive on different threads.
Right. Okay.
And each of these threads still expecting another receive, but there's only one sender here left and doing 2 send, and also happen to be received by 2 receive on different threads, and then they just went into deadlock.
Okay. So I feel this version is harder to understand than the versions I've used, because even I'm getting confused now. But if you go to the previous the one with the code, the solution it was not, you didn't even need non-blocking. You just needed the tag number, the loop iteration. If you used as the tag, that would have worked. So within an iteration, it gets matched. It doesn't go across the loop boundary.
Sure. Yeah, you can. Or you can issue in a rank ID as the tag. So you're saying this thread ID as the tag.
Yeah. Okay. You can also create a separate communicator for each thread, things like that.
Yeah, which we have some examples, and by the way, it could have performance improvement by doing that. But we'll see in the next slide.
Can I ask a question?
Yes.
So what in this code implies multi-threading though?
Yeah.
Right. See, that's the other.
I think it's in the slide title. The assumption is that both threads run this code.
Okay.
Yeah.
But all right. Okay. So I'm not seeing any thread creation or anything. Hence why looking at that. Well, of course. But okay.
Right. So there are 2 threads. So there are effectively 2 instances of these running. Each rank has 2 threads running this stuff, right?
Yeah.
Okay. So
But as compiled and run, this would not be multi-thread.
No, you have to unless if you create.
Right.
Yeah. Just imagine there's a OMP parallel on top of that.
So these are the 2 iterations effectively on each thread that are running.
Yes.
Right. So if the version I had was a for loop, just with the first part, with 2 iterations.
Right.
And the solution is that in the second, the second block that is in red, if you use the iteration number as the tag, that'll also work.
Yeah. So basically, is you can have. So if you have these 2 group communication, you can have the last one has the last group has different tags, I think. Maybe we should revisit what the code was and maybe improve the slides.
Improve the slide.
Yes.
Yeah. I mean, I think the old slide might have been easier. At least I'm used to that side, but it's fine.
Okay. All right. So far, those are the examples with pthread, and the same principle or same requirement also applies if you are using OpenMP as the threading library. So you still need to maintain the thread correctness. So let's look at some examples. Okay, so here is a loop where all the odd iterations doing send to the process itself, and all the even iteration is doing receive from this send. So if I use a OpenMP parallel loop to parallelize this loop, what would happen? Okay, so this would happen. Sometimes it works just fine, and I guess for most of the time it will have some deadlock, because what happens is there's essentially OpenMP library will decide how the loops are scheduled on multiple threads. Okay, and because there's no, if you look at, because the loop is very simple and there's no dependency in between each iterations. So the OpenMP is free to schedule the iterations in whatever order they want. It wants. Okay, from OpenMP's standpoint. So so this doesn't work. One solution is you have to say I want to schedule this loop in a particular way. In this case, it's static scheduling with a chunk size of 1. Essentially, this is asking OpenMP to execute to assign the iterations to different threads in the incremental order of the loop variable here. So thread 0 will get iteration 0, and thread 1 will get iteration 1. So in that case, because the odd-even threads are doing send, receive, interleaved, so there's always someone sending while others receiving, so the program can progress in that way. Then my question to you here is how we can change the scheduling requirement and make sure this program deadlocks.
You can do a static 2 if you want to.
What?
You can do static 2.
Yes. So yeah, that's right. So if you use a chunk size of 2, then it will schedule all the even iterations first, and then everybody is doing receive, and then block there. Okay. So with me so far? Okay. So and you might think, oh, maybe the loop is not the best idea. How about we just make this small piece of code as an OpenMP task? Okay. So it has the same problem because there's no control of how the task is scheduled. So you could still end up with all the tasks that being assigned to the threads are doing send or doing receive and blocks there. Okay. So and the same thing with task loop. Okay.
I'm not sure everyone knows these OpenMP practices well. You should incorporate these tomorrow, right? So a little more explanation about the OpenMP.
Yeah, well, the task essentially is just instead of scheduling the iteration, you have this piece of code as a small task that can be assigned to a different thread and run there. Okay. So task loop is another similar parallel pragma for this. And you might think, oh, it's all because you're using MPI blocking call. So how about I write this in non-blocking, I send, I receive with a wait. And how about this one? Would this work? Why wouldn't this work?
Well, it's the same, right? If you have two that are only two processes that are two threads that are sending, and they are both waiting, nobody's receiving.
Yeah, that's right. So essentially, if you compare these two code, the MPI receive here, let's take this example, is equivalent to MPI I receive plus a wait, right? So it has a wait like right after it, and it's still in this parallel loop. So this is equivalent to the previous code, so it wouldn't work. How about this? Because now we're blocking on wait. How about we just, instead of using wait, we use the non-blocking version for completion check. We do MPI test on the operation I just issued, and if it's not done, I'll just yield. Would this work? I attempt to say this is working, but actually it's no. Okay, so the issue here is the task yield here doesn't always guarantee a task switch. But that is not related to MPI though. Okay, so how about this one? we just allocate 100 requests and issuing them in the parallel loop and just do a wait outside. Will this work? Anyone? Okay, I see some nodding. Will this, and you think this work? Yes, this will work. Okay. Okay, and then what about RMA? The same parallel loop. In the window, we do lock and put to a window and then unlock the window. Is this a correct program?
Don't you do atomics?
No, it's not atomic. It's just a simple put. Look at this lock here. It's lock exclusive. So this actually, this is, well, I guess the title already spoiled it. It's essentially you're in the risk of multiple loop trying to lock on the same target, which for lock exclusive it won't work.
Even it doesn't matter exclusive, right? You can't lock the same target more than once.
Well, but if you do shared lock, yeah.
Yeah.
If you do shared lock, it's
you can't nest them.
Yeah, but in this case, because the lock is exclusive, so it's incorrect program.
So is that because the target is equal to rand, or they're supposed the targets have been arranged so that they're not, so different threads get different targets, then it would be okay?
Yeah, it could be okay, but if your rand give you the same target on two different scenario, and yeah, so so that's all the fun examples we have with OpenMPI, OpenMP. So the takeaways here is you really need to be careful with the ordering, but with OpenMP that might be slightly better because you have this directive to control what kind of ordering the library is running these threads or these parallel loops. Okay, so after that it's hands-on time. Okay, so the project here is, let's take the derived data type version for the Stencil code, and let's convert it into a multi-threaded version. Okay, using a funnel mode. So this essentially is you can have multiple threads. You can do OpenMP. Or if you want to write pthread to update or calculate the data on your local block, and then in between each iteration, you have your master thread or the process in this case to do a communication with your neighbors. Okay, so the first thing you need to take care of is doesn't have the lines. Okay, so essentially you have multiple threads. Then you have to they have to somehow divide the data they're responsible for updating. Okay, so that's the part that you have to be careful of with the threads. But because there is only the master is doing communication, so it won't having a bunch of problems that related to how the communication is ordering and these operations collide with each other and hang. Okay, so that's still start from the derived data type version, and then the solution is available in this threads Stencil funnel. And this is one of the hands-on project. And the next one is if you want, then we can do thread multiple version. Okay. So instead of having the master thread doing communication, now we really divide the data region between the threads, and each thread is responsible for the data communication within its own portion. So if we divide the the region, this is vertically or horizontally. And each thread is, you see this thread is responsible for communicate with its west neighbor, and also some part of data to the north and south neighbor. Okay. And these two threads in between will only do communication to the north and south neighbor. Okay, something like that. So this is the second one. And again, you can, if you already finished, I would suggest you finish the funnel version, because in that case you will have the basic building blocks for the threads already, and then you just have to slide in the multi-threaded communication in there. And remember to initialize your MPI application with MPI init thread, not MPI init, especially in this case, because it will guarantee to blow, I would say. Okay, so should I? Yeah, okay. I have a few more slides related to the performance aspect of multi-threaded. I think I should just finish it first before you dive into the hands-on. So, as I mentioned, the more flexible the multi-thread support is, right, from MPI thread single to MPI thread multiple, the more overhead it will have on the library. So in reality, is if you do multi-thread communication on MPI library, the performance is I would, in my point of view, is far lesser than the communication performance without thread. Okay, so the problem, the core problem related this is if you have multiple thread issuing communication on the same communicator, and the library would have to lock the communicator for each message issuing. The core reason is because we have these any source, any tag, these wildcard receive tags and ranks, right? Because if without saying any special case for the general MPI, in order to support the wildcard receive, the library would have assumed whatever the message is arriving or being issued is the intended order by the developer, which in case of the multi-threaded, it's not true, because there's the thread could be run in different order, and the message could be issued in different order. But in order to maintain that ordering, that strict ordering that the wildcard receive needed, we have to essentially preserve the order, which is in this case is arbitrary depending on the threads. So there's few ways that we can avoid this scenario. One thing is to use different communicators for different threads. Okay, in this kind of, for example, like this. So we have 4 threads, and when they do communication, the communication can go through 4 different communicators. So essentially, you're separating the traffic that belongs to each of the threads. Imagine you can duplicate MPI COM word for this purpose. I can have T0 communicating on MPI COM word, and the other threads are just communicating on the duplicate communicator from MPI COM word. So they all have the same amount of processing there. It's just the traffic between each pair, each thread are kind of separated. So in this case, from the perspective of MPI library, the traffic on each communicator is essentially fall back to a more like a single-threaded case. So in that scenario, the library could optimize the case, because it knows that these are different resources, and the message between them are the ordering is irrelevant. So the And underlying the library could even map these different communicators to different hardware resources to further reduce the contention between the multi-threaded communication. Okay, so that's if you can try to use different communicator, which we also have a hands-on example that you can try this on. So the second thing is, like I said, the reason that we have this strict ordering issue is because these any source, any tag, these wildcard receive. However, if your application, when your application is so complex, it's usually very hard to keep using this and still be insane for most of the time. So one way that we can do is if we have a way to tell the library that saying that I'm not going to use wildcard communication on this particular communicator. And then MPI from the library, it kind of relaxed the restriction on or requirement on the ordering. So, and then the library could further optimize the communication. So this is actually, we can do this through info hint by providing this no any source or no any tag info hint to the communicator. And this is actually being considered for the MPI4 standard, and it's actually already voted for acceptance. So when MPI4 comes out, this is one way to improve the performance of the multi-threaded MPI communication if you don't use these wildcard receives. And also the other way to do this is essentially using a different peer rank and tag. The rationale behind this is the library could be isolating the hardware resource or the internal software queues that are being used for this communication based on the ranks and the tags. Because if you like we mentioned, if you use tags, you can do some level of out of order message matching, which the library could be leveraging on that by saying if it's not the same tag, and I can map them to different hardware resource so they have less contention. Okay, so that's all the let's see. That's all the content I would like to cover on the threading. So the last one is just if you have finished the multiple version for the Stencil code, you can try to improve that using multiple communicators. The performance won't be different in the current MPI, but in future versions, you might see significant improvement in terms of performance. Okay, so let's say we have 30 questions.
So why would you maximize independence with tags instead of by just setting up separate communicators?
Well, it's not whether you should use multiple communicator or separating tags. These are valid options depending on what your application is doing, right? Because you might already be using multiple tags for different purpose. In that case, you probably want to use multiple communicator. So I think I forgot to mention this. So the takeaway with this recommendation is you want to expose the parallelism, the thread level parallelism to the library. So these are the multiple communicators, and the tag rank, peer ranks are just the ways that you can let the library know that these are actually parallel communication that from different thread, which without this, the library wouldn't know. So there's impossible for the library to optimize. But with this information, the library could do something. It could ignore it, right? But if the library is capable, you have a very high quality implementation of the MPI library, it could be doing all these optimization on the line. And I think for now, at least with Intel MPI, they already have some improvement like split communicator, but those are not standard, not MPI standard. So it's specific to Intel compiler, Intel MPI library. So if you use that, you can, if you look at their manual, you see all this information. So here, because the peer rank and multiple communicator, this doesn't conflict with the existing MPI standard. So the library could choose to, at least in our group, we're working on optimizations that these can be beneficial for these cases. And the only thing that related to standard is the no any tag, no any source info hint, which will be part of the MPI standard when the MPI 4 comes out.
Yeah, I was just going to add that it's whatever you do is going to be heavily, I mean, the performance is going to be heavily implementation specific. So you're really going to have to work with either the MPI support people of your implementation or consult the manuals, because there's no standard way, but each of these are valid ways to isolate resources. But how MPI deals with that is going to be heavily specific, at least for the time being.
Is there a specific recommendation for NPitch?
We don't have it yet
yes.
even in a pre-release or master branch. So I think we intend to support both, as far as I understand, both communicators or tags. And there's some way you would hint to MPI that's the way you're going to be isolating resources. But I think the intention is to support both.
Yeah, but look at it this way: even without all those optimization, writing your code with multiple communicator doesn't hurt your performance at the moment. So it probably makes sense if you write a program in this way, because the performance will be the same. But essentially, it could be beneficial in the future when a new version of the library comes out, and boom, your performance get 2x improvement, something like that. So yeah, so I would recommend that when you write multiple MPI plus thread, consider this, okay? So we have, let's say, we have 30 minutes on the clock. Are we going to do? So yeah, okay. So then it's hands-on time. So I would say just do the stencil, do the funnel version first. Do the funnel version first. And later try to improve on it if we have time, or we can continue after dinner. Yes.
Yeah, I was wondering for these two exercises, between the funnel and the multiple threaded one, performance-wise, I assume that if inside the node the threads are properly balanced, the multiple one would be worse, right? Because you have many more MPI codes. Would it be the funneled version actually better, assuming that it's properly balanced between the threads?
Yes, the funnel version, performance-wise, yes, but it's related to the load balance, but it's mostly because the thread multiple version, the multi-thread communication performance is really bad, because in this thread funnel version, essentially you can think it as a single-threaded version for communication, which performs really good, and only the calculation part is parallelized with threads. But in the thread multiple version, because the communication is multi-threaded, so you can expect a significant degradation in terms of performance, regardless how balanced the data is.
So then I would always prefer to go for the funnel one in principle.
Yes, for if you write program today, but we are trying to improve we'll keep improving the performance for the thread multiple case, so it won't suck as much as it today, and so you can use that, because it's more flexible model as you can see it, because you don't have to say I finish this chunk of work and do some communication and then finish the next chunk. It's all could be overlapped. The second hybrid programming model I want to talk about is MPI plus shared memory. Okay, so as you have seen when we cover in the part for RMA, there's a MPI win allocate share, which creates a shared memory, what we call the shared memory window. Essentially, this is allow different processes to create a shared memory region and also use many concepts of the one-sided communication. So the rationale behind this is some application today trying to use or they want to use MPI plus thread, not because they trying to reduce the complexity of the communication or trying to or the download parallelism with thread will bring them huge improvement in terms of performance. It's because they're trying to share data within one node. Just like the example that's with QMC pack, right? If you are able to share this huge B-spline table among the cores on the same node, you save a lot of memory, which can be used for either running a larger problem or something else. Okay, so then the thing is, if the only goal of using thread is, if your only goal of using thread is just to share data, why not use shared memory? Because if you use thread, because everything is by default shared, so you have a lot of problem with thread safety and all other stuff. But if you just you just have a huge table that you want to share between the process, one way you can do is with MPI shared memory. Okay, so essentially you just call this win allocate share, but there's a catch. So before you create a window, create a shared memory window, first you need to figure out which processes are on the same node. Okay, so simply put, if you took MPI COM word, which have 1 million processes that's on 100,000 nodes, and you're trying to do a share MPI win allocate share, it won't work. It's impossible to create a shared memory across node. Well, at least for now. So the first thing you need to do is figuring out which process are on the same node. The way we do that is through MPI COM split with a COM split type with a special type called COM type shared. What happens with this function is it will take your input communicator, which in this case is MPI COM word, and split into subcommunicators that only contains the ranks that share the same node. So let's say we have 10 processors per node and we have 100,000 nodes. And the results for calling this function is you will have a subcommunicator that only have 10 processes, and those 10 processes are yourself and the other 9 processes that share the same node with you. Only with that subcommunicator, then you can call the MPI win allocate share on it. It will create a shared memory region among those 10 processes. Okay, so if you then after that you can start doing all the fancy operations on it. So the difference between a regular RMA window and the shared memory window is actually not much, right? So the memory region in the regular RMA window is separated, even if these two processes are on the same node, because it's within their own memory address space. So it's still private to them. But with the shared memory window, you create a shared memory that is visible to all the processes on the same node. And that's the first difference. And second difference is how you access those memories. Okay, so with regular RMA window, you can do load store to your local memory, but if you want to access a remote memory through the RMA window, you have to use the put get, or if you want atomics, you can use atomics. Or you can use the get accumulate, something like that. But with the shared memory window, because essentially it's shared memory, right? So you can just load store into it. And if you need to do atomics, you can use the native atomics to operate on this. So you don't have to, if you just do load store, if you just need load store, you don't have to do put get, although you can in this case, but it's not recommended because there's overhead come with it. If you just need the load store, you can just do that. Okay, so as I mentioned, you need to split the you need to create a subcommunicator that only gives you the group of processes that's shared on the same node. So this is the com split type function you will need. So and what you need is you need a communicator as input, and the split type in here will be com type shared, and you can put some keys, or if you have info hints you want to provide it, you can put them here. And what the new com will be the subcommunicator for the shared for you to create the shared memory. And then there's win allocate share. Okay. So essentially, here is a very short example of how to use shared memory window. Like I said, you can do load store directly to the memory region, and also because it's although it's a shared memory, it's still an RMA window. So all the synchronization and these RMA semantics are still, you can still use them on this shared memory. Okay, so a few things to keep in mind. When you create this, each process can say I want a different amount of memory being allocated or being allocated in this shared region, and you can some process can even say I don't want to allocate any memory. Okay, so think it that way. Maybe you have one rank, want to create a huge table, and you also need to initialize that. It can also it can say I want to allocate this shared region which I own the entire part of it, and then everyone else just contributes 0 bytes, and I'll just initialize it, and everyone can just read from it. That's if you want to do that, you can do that. Or maybe in our case, if you think collective initialization to the shared memory is more efficient, you can say everyone can just contribute their own part and combine as a shared memory. Okay, and so another thing is for the shared memory, the MPI standard doesn't specify where the memory is being allocated, or whether the physical memory is getting pinned. So if you want to, this could be an issue if if your machine has multiple NUMA node, where you might want to allocate shared memory only for the processor that shares same NUMA node, so the memory access is faster. Because if you have a process running on a different NUMA node and trying to access the memory belong to this NUMA node, there's overhead with the inter-NUMA access. Okay, so but MPI doesn't give you any control on that. But as you will see, there's with topology and other improvement in MPI, you will be able to query those information, and you can make your own decision, and even create subcommunicator per NUMA node so that you can create shared memory just for those essentially within the NUMA region. Yeah. And also the shared memory is by default contiguous on the allocated for the communicators. That's very brief introduction about shared memory. So we plan to have we have a hands-on example that you can try with. So essentially, is taking this Stencil log put version, the log put version of the Stencil code and convert it into a one-use shared memory. So what happens is you just on the same node, essentially, assuming these 9 processes are on the same node, but you can create a grid in the shared memory region. You can allocate a shared memory window and create a shared memory for storing all the data that these 9 processes has. And then instead of doing communication, you can just simply do load store from a remote process. Okay. So that's that. So then the question is, which one should I use, right? So like I said, if the one reason that I would recommend shared memory over MPI plus thread is thinking about what you really need. If the threading model doesn't give you much than just sharing data, you can think about using MPI plus shared memory, because you have the benefit of sharing data among process, and at the same time you have the performance of single-threaded MPI communication. Okay, but if your application need more than just sharing data, for example, many applications use OpenMP because the program model makes it really easy for programming across multiple core or parallelize their problem. So with that, all those easy to use parallel construct does not exist with MPI plus shared memory. So if that's all you need, you should use thread. Specifically use OpenMP in that case. Okay, and it's also depending on what kind of machine or what machine you have or what MPI that machine has. So if the machine has a very old MPI which only supports MPI 2 standard, you may or may not have some of the feature. Then in that case you may think, what can I use? Maybe shared memory is not an option or something else. Okay, so with the shared memory, there's also like the shortcomings I just have to mention here. So use MPI shared memory. Everything has to be have to go through the MPI call. So you cannot use currently you cannot use say I do mmap to create a memory region and then create a shared memory window on top of it. It doesn't work that way. Okay, so it's also limit the usability that if you want to use shared memory for some external library where the external library have no idea what MPI is doing, it might be a problem. So it's more restrictive use cases with MPI plus shared memory. So yeah, so that's all. I'm not going to ask you to do the hands-on right now because I still want to cover the MPI plus Accelerator. But if you want, you can finish this later, maybe after dinner tonight, if you want. Okay. So is there any question about MPI plus shared memory? Yes.
Are there any situations you can see where you'd want to use both? Or would it usually be one or the other?
Well, using both, I wouldn't. I never thought about that. Okay, so because my rationale is like if MPI plus shared memory is enough for my need, then why use threading? Right? if only MPI plus thread or MPI plus OpenMP satisfy my need for all the parallelism and other programmability requirement. And then at that point, your memory space is shared already, right? You're in the same memory address space. So you don't need to create a shared memory region. I mean, the extreme case I can think of is, let's say your compute node have multiple sockets, and for your local performance reason, you want to run one MPI process per socket or per NUMA node, and then OpenMP parallelize it. And at the same time, you want to share some data across the NUMA node. Yeah, I guess you can do that. I don't see any reason that is against this use case. But if your problem requires this kind of setup, you can do that. The library doesn't prevent you from doing that. Yeah. Any other questions? Okay. Then we talk about the MPI plus accelerators. Okay. So speaking of accelerators, I think most of the talk that we're going to cover is specific related to one type of accelerators, which is GPU. So in real system, you might have FPGA as an accelerator, but that would not be covered in this topic. Although we can talk about it, but it's kind of different from GPU. So the whole tutorial here is centered on the GPU. So assume a GPU as an accelerator. So so the reason we have GPU is because of this performance, the high performance over power ratio. So because we supposed to grow the machine by magnitude of, we want to grow the performance by 10 times, but not increase the power consumption by 10 times at the same time, right? So and CPU is, comparing to GPU, is not so power efficient on some of computation tasks. So that's why more and more HPC systems today are adopting GPUs, even multiple GPUs per compute node. Okay, so then the questions become, how do we program them with MPI? Specifically is how to move data between GPU and CPU, or from local GPU to a remote CPU, or even to a remote GPU. And how can MPI do that, or what is needed for MPI to do that? Okay, so the simple answer is, if you have a modern GPU with the latest driver, latest libraries, and you can just use the memory buffer on the GPU as any regular memory buffer, and put them into MPI call and send receive message using it. But the real answer is, if you don't have the latest GPU, latest library for that, it depends. You can do some of the GPU-aware things to a certain level, but maybe not in ideal performance, or there's some limitation come with it. Okay, so assuming you have the library, the biggest challenge in doing this is essentially the awareness of GPU in MPI. So here I'm just using CUDA as an example. So what happens is, when you do MPI communications, you take a memory buffer, but with GPU in the mix, the memory buffer could be on your host CPU, your host memory, or on the GPU memory, which at most basic level, you have to figuring out where the memory is and decide what to do. Okay, so But with the latest CUDA is largely with the latest MPI library, can be fairly CUDA aware in this case, so it can automatically handle this case. But let me tell you a little bit more about these limitations. So without all the CUDA awareness in MPI, then what happens is if I have a code like this, so I do some computation on GPU, I have to explicitly copy from the device buffer to the host buffer before sending those data across the network. So you have to do a CUDA copy, CUDA mem copy before you do send. And on the receive side, after you receive something, you have to explicitly copy them from the host CPU, host memory to the GPU memory in order for the GPU to do further computation. And it is the same if you're not using CUDA. If you're using OpenACC, it's similar without any CUDA or generally saying accelerator awareness for the MPI. Okay, so this scheme causes a problem is because you have multiple data movement, and while your system is moving the data and doing the communication, your GPU, there's no overlapping of the computation and the communication because everything is kind of serialized because your GPU might be finishing this computation and then data is being moved and sent while it's also waiting someone else to send him more data and to do more computation. Okay. So and because the requirement that the data is being ready before send, so you can't even use something like CUDA mem copy async to asynchronously move the data. It doesn't work because if you call mem copy async here and then you could do MPI isend, the data may not be copied to the host memory, so you have no idea what is being sent over the network in those buffers. Okay, so like I said, the downside of this is because your GPU will be waiting for data and it will be idling around, so it won't be very efficient, and the entire execution model becomes a very inefficient block, synchronous, and wasting GPU time. Okay, so a CUDA-aware MPI implementation, have some basic requirement. The one is the unified virtual address. Okay, what unified virtual address is, if you look at the figure here, the non-UVA version versus the UVA version, the difference is if I have a host memory and I have two GPU memory, without UVA, they're all in their separate memory address space. So if I essentially it's the data you have to copy the data around, and with UVA, because they're in the same memory space, you can we can have if we're given an address, we'll be able to figure out where the address lies. It could be in the GPU memory or it could be CPU memory. You can know, at least you can know that. And then depending on what kind of GPU direct that your hardware and driver supports, you may or may not need to copy the data between the GPU memory and the host memory. But the basic requirement is at least you need to have the UVA, and given a memory address, you can query whether this belongs to CPU or belongs to the GPU memory. Okay. So if you have the on top of the UVA, the most basic support is that now, because I have the way to query it if an address is on CPU or GPU, then you can remove the explicit memory copy that used to sit in here, and just take this buffer, this pointer to the buffer, and give it to MPI. So MPI internally can look into see whether this is a GPU buffer, and if it is, it can copy the data into the host memory. So this is not a performance improvement, but more of a programmability improvement. So you don't have to worry about that. But that is because the network card or the GPU doesn't have the way to directly dump the data from GPU memory through the network. Okay. So in that case, you still need, but the good thing is you can automatically move the data from a GPU pin memory to a network pin memory. So for the communication. Okay. So that can be handled easily. And if you have more advanced hardware, for example, if you have GPU Direct 1.0, which is around 9 years ago. So in that case, you don't need a GPU pin memory in the main memory as an intermediary. You can the data can be DMA'd from the GPU memory to the send buffer, to the pin memory for network communication. And if you, but this case, as you see, it's better than it used to be, but it's still not ideal. And plus, you'll have require some kernel driver update, but that was like many years ago. And right after that, there's GPU Direct 2.0, where you can essentially this provided a peer-to-peer data movement for the GPU on the same node. Okay, so you don't have to go through copying to main memory, then to another memory. But as you may know, that if you have the latest GPU with the NVLink, the GPU memory of multiple GPU are in the same image. They themselves will be able to do this even without MPI. So so there's that. And if you have the latest and greatest GPU that is available, starting from 2013, and you use a CUDA library that's higher than version 5, what it has is it can do RDMA through GPU memory to network. So basically, avoid all the copy through the host memory. So this is so far is the most efficient way with GPU direct RDMA. But this is only available in the latest hardware and library. So to summarize here, all those are happening under the hood. Okay, as long as you have a CUDA aware or GPU aware MPI library, where you can take a pointer to a buffer, a memory address, regardless where the memory lies, where the actual page lies, and throw it to the MPI. MPI should be able to figure out what is the best way to transfer the data. So as a programmer, as long as you're using the new library, new hardware, the MPI aware, the CUDA aware MPI should be able to do that. And all those information is just for you to know that these could be happening if you don't have the latest hardware, and there's you may or may not have some performance issue due to this reason. Right. So even with some of the earlier version, even with the latest hardware, if you don't have the latest CUDA library with it, you may still not be able to use something like GPU direct RDMA, which you will see performance degradation. But having to know what might be going on under the hood, at least give you a way to look at some point where you can look at if you're running into performance issues. Okay, so that is the last slides of the hybrid programming model. Is there, if you have any question? Yes.
I got a question on the last CUDA 5, I guess, last slide.
This one?
Can GPU do computation while the memory is being transferred to the network? Can you do both at the same time?
Yeah, they can. Yeah, so yeah.
Should we expect
So actually,
focused on CUDA here, should we expect these same performance improvements in MPI to appear for AMD GPUs and the Intel discrete GPUs by the time that Frontier and Aurora come around?
Yeah, I think the correct answer is depending on whether they support RDMA from the GPU memory. I assume they would add something like this. If that's the case, I would say the performance would be.
Whether or not you can actually download and build an MPI yourself that is able to do it that may not be possible at the time those systems arrive, but the vendor-supported implementation, I would expect would support that. Yeah.
Yes.
So there are non-MPI, before I understand, NVIDIA, NCCL libraries. Can you comment on how that's different in terms of performance compared to an MPI-based implementation? So NVIDIA claims to use a topology to build an NCCL collective communication library, and I was wondering how that is different from this.
Actually, I don't think we have any number comparing those two. But NCCL, that's intranode communication.
That's what they recommend for multi-GPU in their website, but again, they don't have benchmarks with CUDA or MPI. So.
Yes, well, I would say that when NVIDIA says multi-GPU communication, it's probably referred to multiple GPU on the same node.
It works multi-node too. I think it's probably.
But it's probably over InfiniBand or something?
No, I mean, it could be both NVLink or InfiniBand, yeah. I think it's whatever it is, I mean, it's what part of NVIDIA's secret sauce. So it's, you know, as far as I know, those are probably, you know, is that a library open source? Do we know?
I don't think.
But I mean, collective implementations is kind of, collective algorithms is one way in which MPI implementations can differentiate themselves. So if they have specialized algorithms for a particular topology or particular, you know, their thresholds are set based on the communication properties of those GPUs, that's one way that they can kind of differentiate from an MPI. Now, an MPI might eventually add similar types of collective implementations to compete with that, but.
So theoretically, if you had replaced CUDA or MPI with GPU RDMA for a different GPU vendor, then everything the framework should be the same. So if you write the code with RDMA for GPU and MPI, it should run theoretically on AMD.
More or less, yeah. That's the intention.
Yes. Any other questions? And on even on MPI plus shared memory or plus thread?
Yes. So then MPI in principle can use NVLink if it's available.
MPI, can you repeat?
If it will be able to use, if it's aware of it, it will be able to
use NVLink?
And to connect it in the GPU, so is it possible?
Well, if you do that, I assume the GPU are at least can do DMA from one GPU memory to another one. I think if I'm the NVIDIA driver writer, I will make it through the NVLink, I think.
Yeah, I think that if I understand correctly, so MPICH supports this through the UCX communication library, and there's 3 different ways to do transfers to and from GPU memory within UCX. One is CUDA memcopy. That's usually for small messages where the benefits of RDMA, you know, or the overheads of RDMA kind of outweigh just copying the host memory and communicating from there. The second transport is this IPC mechanism, CUDA IPC, which I believe will use NVLink if possible for you know, GPUs that are connected in that manner, presumably on the same node, though it may work off node as well. I'm not entirely sure. And then the third is if you have a sufficiently large communication, it will use this GPU direct RDMA transport. So again, the thresholds are kind of hardware or implementation specific, but I think that yes, MPI will use NVLink if it makes sense for that particular communication. At least that's the way I understand it.
So for MPI plus Accelerator, a lot of companies have this higher level abstraction, like we mentioned PyTorch. Do you think like if, say, for non-machine learning people, like they can also use this higher level abstraction for MPI plus like GPU? Because there's also like a workshop on alternative to MPI plus X, right? So is that a trend?
Higher level model, like, well, I think these are not the. I think this is a little bit hard to say what's going to happen in the future. Whether there's going to be a higher level abstraction that replace MPI with other stuff. Because I think many of the high level construct are so far is focusing on providing a better programmability, other than just going the right MPI calls directly. But internally, they could still be using MPI for optimal communication performance. I mean, if there's, I would imagine if a program model has a communication need that is so different from what MPI is providing today, then it could choose to put them on network libraries such as UCX or libfabric directly, rather than go through MPI. But in that case, they will still have to figure out their own CUDA aware, or in the case with UCX, it might be easier. But I wouldn't say whether those high-level program model are going to replace MPI plus CUDA, MPI plus Accelerator, because I think they are not on the same playing ground.
Okay, we're getting to the last topic of the day, which is about process topologies and sort of topology mapping and the associated neighborhood collective operations. So the basic idea here is in process topologies or topology mapping is to map processes to processors or to cores in a way such that the communication, whatever is the communication in the program, happens among nearest neighbors or happens in a nearby domain where communication can happen more efficiently rather than going randomly across the machine anyway. So if you know the communication graph of the program beforehand, who is communicating with whom, and you know the machine topology or the machine architecture, you should be able to map that onto the machine in some way such that most of the communication is, say, local within a node rather than going across nodes or in some other way. In general, it's a hard problem to do the mapping. It might even be an NP hard type of problem. But in many cases, it's better than just doing the default mapping or some random mapping. So what are the ways you can do that? The first one is you do it at allocation time itself. When you're submitting your job or when the job is being run the first time, if the user can specify the communication pattern in some way, then the system could be able to place processes in a way such that those that communicate more or more frequently are nearby in some sense. It turns out that this kind of method is not widely supported, and there may have been some systems that can do some parts of it, but you don't find that functionality commonly provided. So the other method that MPI provides, and it has provided from the beginning, is to do what is known as rank reordering, or to change the rank of a process such that you're not physically moving the processes, but you create a new communicator in which a process may get a different rank, so that they are communicating among in a domain where the communication is in a neighborhood or nearby, so that you're not going across the system for communication. So the way this is done typically is, let's say you're doing a nearest neighbor communication in a Cartesian topology, like in our example. So it's all just a nearest neighbor. So you want to map that onto the underlying process. So in MPI, at the start of your program, you can create what you can tell MPI you want to create a Cartesian topology, and you can specify the size of it, and it's a 2D mesh and the number of processes in each dimension. And MPI will return you a new communicator in addition to COM world. So when you start, you always have MPI COM world where the ranks are 0 to n minus 1. But it returns you a new communicator which has a Cartesian topology associated with it, in which the ranks could be reordered. So somebody that was rank 5 in the original one may not be rank 5 in this new one. It could be something else, or it could be the same. And it's actually a user parameter. Do you want it to be reordered or not? In general, it's a good idea to do that, because if by the reordering, if you're getting a better mapping, then you stand to win. And from then on, from the beginning of the program, if you use this new communicator, then you're ensuring that the communication is within a neighborhood, or it's not going across the whole system. If you did it somewhere in the middle of the program, then if you have already computed some data using an old process numbering, and now you have new numbers, you might have to move data around to get it into the new mapping, and then start from there, which is not, it's not a good idea. So the concept is, let me see. If you have a program where the communication is like this among ranks, this represents some weight. That means, let's say it's the number of times they communicate or the amount they communicate. So the larger means there is more communication happening. So here 5 and 6 are communicating a lot, but 3 and 5 don't communicate at all in this program, and so forth. Then a naive mapping where you just go 0, 1, 2, 3, 4, 5, 6, 7 among the nodes will result in a lot more inter-node communication based on this kind of communication graph. Whereas if you had a mapping like this, where it's 0, 3 on this node, 1 and 2 and whatever, there is a lot less inter-node communication, which is slower than communication within a node. So how do you go from this to this? So you could call an MPI topology or a graph topology or constructor, a creator function, where if you specify these edges and this kind of graph and the connectors, it will assign a new communicator where these ones, where their ranks will be different. So the process doesn't move, but what was 0 in the old one remains 0, but what was 1 in COM world is now rank 3, and what was 2 is now rank 1, and so forth. So you get a new rank, new mapping effectively, and then you follow the communication in the program, and then there's a lot more local communication happening here. Is this clear? So there's no migration of processes. It's just a different numbering that is a better fit for the communication pattern.
So how does the data associate with the different ranks?
Yeah, that's correct. That's why I said you typically want to do it right at the beginning of the program, almost immediately after MPI init, before any data is generated or read from a file or whatever. So instead of doing any computation in this model, you begin your computation with this ranking. So you're going to use the new communicator, the graph communicator that's returned to you, and don't use MPI COM world at all. If you used MPI COM world for your communication, you would end up with something like this. If you did it in the middle of the program, then you would need to move data around because you have partly computed with this kind of mapping, and now if you want to use this, then your data is not in the right place. You'll have to move data around, which is expensive, so you lose. Yeah.
So this requires that I can construct a graph of my communication pattern?
Or at least be able to specify. And there is a graph topology constructor in MPI where you can specify these edges and who communicates with whom and how much. So how do you find that out? One is either you know it just based on your pattern, or you could run your program once just to get that information, and from then on, you know that and you don't need exact numbers. These are all somewhat relative numbers. You need to know who. You just need to know the who communicates with whom more frequently than others. So and that can help. Yeah.
What if we have dynamic domain decomposition, where after every few time steps, the neighboring processors and the amount of times they actually communicate with each other is varying?
Yeah, so that's a different kind of problem, and I think the libraries tend to deal with that by moving data around and doing it. I don't think MPI directly, at least these topology creation functions directly help with that. So you typically use a library on top of MPI that does, somehow manages that for you and maybe reshuffles data a little bit so that the computation is better balanced and so forth. Okay? So that's the idea. Similarly, this is another example where you're a mapping of this kind of application topology where 0 communicates with 1 and 3 and 3 with 2 and nothing else. If you did a naive mapping where 0 was here and where is 1? 1 is here, 2 is here, and 3 is here. There is a lot more communication among the, you're going over a longer distance for the communication, whereas if you did it this way, they were all just 1, 1, 1 across the links. So based on the communication pattern and the topology of the machine, you can do a better mapping of ranks of processes to the actual nodes. So what MPI provides are some convenience functions to create either a general graph topology or a Cartesian topology. And we'll look at the Cartesian topology because it maps with the example and it's easier to understand. And it also provides some convenience functions, particularly for the Cartesian topology, because you need to know the rank. Each process needs to know where it's located in that 2D mesh. It needs to know who are its neighbors in all the directions, the actual ranks of the neighbors, because all the communication you do is in terms of explicit ranks. So you need to know the target. So there are functions that MPI provides that you can use to figure all this out instead of calculating it yourself. In the code example, all that gets calculated pretty much, who's your neighbor and so forth. Then MPI 1 had a graph topology function in which each process had to specify the entire graph. I mean, not just its own connectivity, but everyone's connectivity, the whole thing, which is, with MPI 1 days, that might have been okay because systems were not that big and so forth. Now, if you have 1 million ranks running, everyone specifies this million node graph, which is, it's not scalable. It takes up too much memory. So MPI 2.2 came up with more scalable approaches for specifying the graphs in a distributed way. So you can specify just your neighborhood and so forth. There are 2 ways you can do it. And in MPI 3, they added collective communication functions, just 2 of them, that can communicate among neighbors. So the example that we are doing, that's a nearest neighbor communication. That could be done via a collective function, like a neighborhood all gather and so forth. So that helps you to do the nearest neighbor communication in a more collective way or more optimized way. At least the implementation has the opportunity to optimize. So let me just go through the functions that are there. The first thing is, these are convenience functions for Cartesian topologies. One is, if you're running on some number of ranks, say 1024, you'd want to know how to decompose it into, say, a 2D mesh. What is the right way? Do you want to do 512 by 2? And that's probably not right. That's too long and narrow. You want something as square as possible. So you can ask MPI to suggest this kind of what the ideal thing should. So the input would be the number of ranks or number of MPI processes, and also the number of dimensions, and it will return an array where it will try to give you as square a decomposition as possible. That's just a suggestion to you. So if your input is 64 and number of dims is 2, it would return this in this array. It would return 8 and 8, which is 8 times 8 is 64. That's a square mapping. That's easy. You could do it yourself. But if you had some bigger number, 3,260, what would be the best 2D decomposition or 3D decomposition? That's something you can ask. You don't have to follow it. You could use your own, but it's just a convenience function. The next function, the function that actually creates this Cartesian topology, or the communicator, is MPI cart create. So one way to use it is you first call MPI dims create, the function we just saw, which returns, given the number of processes and the number of dimensions, returns an array with 3, it'll have 3 numbers in there corresponding to the x times y times z number of processes in each dimension. That is one of the parameters to the cart create function. The other one is the number of dimensions. This parameter just indicates, this one, the periodic, is whether the boundary processes have a wraparound. That is, when the boundary process at the top wants to communicate with its top neighbor, there is no top neighbor. So does that mean it communicates with the one all the way at the bottom or not? So if you say it's not periodic, then it will assume that there is no neighbor at the top, and similarly, there is no neighbor all the way for the last row and on these sides. And we'll see where that comes into play. And I'm forgetting what this 0 parameter is. This parameter is whether to reorder or not. So here it says 0, don't reorder. That is, I'm just using this for convenience to get the topology information, who are my neighbors. But typically, you could pass a 1 here, which means it will try to change the ranks, give you one with potentially a different mapping, so that might be more efficient for a Cartesian topology, like we saw in the graph where the mapping changed, the communication became more within a node than a cross node. So that's the cart create function. So it returns a new communicator which has this Cartesian topology sort of associated with it. And then there are, so these are the convenience functions associated with it. One is, if you are given a communicator that is a Cartesian, that has a Cartesian topology, how many dimensions are in that topology? You can query with this function. It will return the number of dimensions. Then you can get the size of the dimensions. Is it an 8 by 8 or is it 16 times 4, or what was associated with that? So for example, if this was passed to a library and the library doesn't know what it can query and get all that information. And then these functions translate coordinates to rank and rank to coordinates. So if you are in this 2D mesh, if you are at a particular index, what is the rank of the process at that index? Normally, you would have to calculate this yourself. You can get it through this function, and vice versa. Given a rank, where is it located in this 2D or 3D mesh? And then the other thing you want to know is, who are your neighbors? Who is your neighbor in the up, down, left, right? And you can even find the neighbors at a distance of more than 1. So you could, who's the neighbor at a distance of 2, 3, or 4? That also it can tell you. So this is the function for that. The direction means, do you want it to be in this direction or this direction? Or it could be in the third dimension as well, which as you choose. The displacement is, you want your immediate neighbor or one beyond it or another beyond it and so forth. And then you pass the source and you get the rank. So typically, if you want to know who's your neighbor, you give your rank as the source rank, and you will get the rank of that neighbor. Now, since this is a parameter, you could even give somebody else's rank and know their neighbor, who their neighbors are. So it's that flexible. All these calculations you could do yourself, because these are just, given the size of this topology, you can calculate it, but it can be error prone. So these are just convenience functions. So given a I'm not going through the graph topology example because that's a bit complicated. There are a whole bunch of parameters to provide, but you can look it up in the MPI standard. It's a similar thing. You have to specify the edges and the weights and everything, and then call the graph creation function. The neighborhood collectives were added to MPI in MPI 3, and there are two of them. There is an all gather, and there is an all to all. So the all gather is like doing an actual all gather, but instead of everybody getting the result, it's only the nearest neighbors at a distance of 1 getting the data, and everybody gets the same data. So you can use it in a stencil-like computation. And the other is the neighborhood all to all. So again, this happens within the neighborhood where the communicator has, you pass, the communicator that you pass has a topology associated with it. But all to all means there is a unique data that is being sent to each process. And there are non-blocking versions of these functions as well. So there is an I neighbor all gather and I neighbor all to all. So these are similar to the other non-blocking collectives. There's no difference. Just to summarize this section, MPI does not expose information about the network topology. So as such, it doesn't tell you about the system. It expects the user to inform MPI about the communication pattern, and MPI tries to do a good job of about the topology mapping. And there are convenience functions for, particularly in Cartesian, it's useful. And these topology constructor functions can also remap. Not all implementations will do a good job of remapping, or they may not even do the reordering. You might get the same data back. And the neighborhood collectives are doing the nearest neighbor communication in a collective way. Again, it's implementation dependent how good it is, whether you'll get good performance or not, I would say. I'm not sure how many of these, how many of today's implementations really optimize the neighborhood collectives, but it's something worth exploring. So we're coming close to the end of the slides portion of this tutorial, and we can go back and revisit what the examples we covered. I'm sure you didn't go through finish all of them, and then we have time between now and dinner to work on them. And even after dinner, if you still have energy, there's yeah.
I was curious, do you have a recommended visualization tool for the network topologies?
You want to visualize the actual network topology,
or I mean to construct a graph to see if you're inefficient, or
so some of the tools that you will it's on Wednesday, I believe, will tell you the communication pattern in your program. So you can run your program once, and it will generate statistics and traces that will tell you a lot about your program.
I think also that Scalable allows you to visualize the patterns of the prompts, like in a GUI way.
Okay.
Yeah, Tau also has its own. They all have slightly different ways of doing it, but these tools have advanced quite a bit over the years now, so they're quite sophisticated. Just using them may not be that trivial because they're quite complex tools, and that's why there's a whole day associated with them. And there are vendor tools also, so there's something on, there's a Cray, I think Cray is presenting on Wednesday as well for their tuning, and Intel has something. And there's HPC Toolkit, there's Tau, and there is the Scalable and others from Germany that are there. Yeah?
Yeah, I was wondering because in one of our applications we actually use a 3D Cartesian topology, and it's very useful.
Yeah.
But to be honest, I don't remember if we said the not reorder or reordering.
So you actually use the cart create function?
Yeah.
Yeah.
But then I was wondering if you said when you created to reorder.
Yeah.
what does it do? I mean, because it doesn't know what communication pattern I have inside.
No, but you have said it's Cartesian, right? So Cartesian is like it's a restricted graph topology where it's all the communication is near, in like a 2D or 3D nearest neighbor. So by saying Cartesian, you have pretty much indicated your communication pattern, that you're not going to go long distances outside the nearest neighbor kind of thing.
But even if I have Cartesian, if, for example, if my communication is always, let's say, across the x coordinate, maybe it would be more efficient to actually store all an x coordinate row inside a node instead of the neighbors in 3D.
Yeah, true.
So I don't know if there is a way to actually.
So if you have a special Cartesian one where you really have one dimension, then you could use the graph approach to indicate that, because that would be a more clear thing. But if you have, the regular Cartesian is when it assumes that you need to communicate with your nearest top down, left, right, and maybe in the.
And then it tries to divide.
And it tries to map that. So if the machine itself was in a mesh, and there used to be machines like that had a mesh structure, that's a nice, easy mapping as well. But even on the other machines which are different network topologies, there is a way to map those so that it's more efficient, that communication.
And there is a way to actually know what reordering it did?
Yeah, you can print it out, right? You can, because now you have two communicators. You have the COM world that is always there, it's never going away. And you have this new that you have just created called the Cartesian topology communicator. Each process can compare its rank in COM world with its rank in this new communicator. And then you'll know if it's done some remapping. Yeah?
Does the Cartesian communicator take into account if it's not Q decompositions?
If it is not what?
If they're not cubes. So like if I have more communication with one neighbor as opposed to my others, because it's not a cube.
It won't know that by default, because there's no way for you to indicate that your Cartesian topology has more communication in one dimension than the other.
No, because I'm just saying, like, so like in your example, if you have a 64 node mesh, if you have 100 node mesh, you can't cut that into squares.
Right, there,
so one of them will have more nodes connected to another mesh.
Well, 100 you could do 10 by 10 or something like that, right? But you want to,
but if you don't.
Yeah, if you don't. So when you say MPI cart create, all you're telling it is that you're in this number of dimensions mesh, you are roughly going to communicate equally among the neighbors of that. You're not. There's no way to say there is more in one dimension than the other. So if there really is more in one, it's a special Cartesian where you're doing more in one than the other. Then the graph might be.
Well, that's not really what I'm saying.
Yeah.
Like, so say for our example that we're doing here, our blocks are rectangles. They're not squares.
Yeah.
So we're doing more communication with
in that
north,
way,
south, east, west.
Yeah. Again, the graph would be a better way if you want that level of precision. The Cartesian just assumes that you're roughly communicating equally with the nearest neighbors.
There is a proposal in the MPI forum, though this is obviously far out, but there is a weighted Cartesian, creation function being proposed where you might be able to give MPI a little bit more information about your neighbor communication than the current APIs.
Yeah. Okay. Yeah. So these are just some conclusions and a reminder of the pointers and the tutorial book. So what I wanted to do was, let's see. Let me just go back all the way to the beginning and do a search on exercise to quickly go through all the. Come on. Yeah. Okay. So the first example was you take the basic code and use the vector type in there. That was relatively easy, I think. The next one was after the collectives was to use instead of point to point, you use a collective function, and that is all to all v. All to all v, you can look up all to all, do a web search for MPI all to all v, and you'll find the syntax of it, and so you'll know how to. Of course, the solution is also there, and you can find it that way as well. But you can just look up the syntax, and it's straightforward after that. There is also a version that says use all to all w, which you could try all that. All to all w is a generalization of all to all v, where you can have multiple different data types in your. So this is just for experimenting with. You can do that. Then the next exercise was in the RMA, and there were I think 3 or 4 in there. One was to with RMA fence synchronization, use MPI put to do the communication. Then the next one was the same thing but use MPI get. So that should be easy. If you get one working, changing from put to get should be relatively straightforward. The next one was using the lock all, unlock all type of synchronization, and you can use put. Here is one case where you might need a barrier because there's no way to know no way for the target to know that the data has been put on the other side. So unless you have the barrier, you will not know that the data is there. You could use some other form of synchronization, but you need something there. So that was that. Then came the threaded examples. This was the stencil in the funnel mode where the solution has got too much OpenMP in it. I think that somebody, some student or somebody has went in and put in a lot of OpenMP. There might be some bug in there, but you don't need that much is not needed, I think. And then the second one was, is this the same one? The stencil in the thread multiple mode, right? This is the second example. And then the other one was stencil with independent communicators, right? Then the stencil with shared memory. So these are a little harder. You might need to look at the slides again to remind yourself how this shared memory is done. And that's it, right? Yanfei, we covered all of them here. So pick the one where you left off, or in the one you want to. You can search for exercise in the slide so that you can find all of them, and the solution is also there, so you can you can look at that to make it a little easier. Otherwise, it can get a bit tedious, and we are around as well. So the dinner is at 5:30, and there's a dinner talk. So roughly 5:15, 5:20, we can start winding down there, and then 6:30. If you're not too tired already, we can continue some more. I know these days are quite long, and every day they go from 8:30 to 8:30 p.m. if you do the after dinner hands-on.